Okay, so the topics for the exam is cardinality and Godel, so things like this, or uh, questions that look like this. One or the other will pop up on your exam. And that's the first topic. Second topic is regular expressions. So um, trying to construct regular expressions like in this example. And then third topic is telescope as context-free grammars, so generating things like this. And the last topic is finite state automatons. And then I'll also go over telescoping, telescoping with context-free grammar. And that's pretty much the whole exam. So let's start. So we'll start with the Godel numbers.
I have one question. Where can I find these notes?
What notes?
I mean, PDFs you're using?
These are old exams.
Oh, okay.
She'll post the answer key after every exam. So I just have a couple. But there's a lot more. But those are COVID exams. Like those aren't that good to study off of. But like last semester's exam is a good thing to study off of. I don't have it on me right now, but if someone sends it, I can look at that also. But the topics are all the same. So we'll start with cardinality. We'll start with Godel numbers. Okay. So the way the reason you learn Godel numbers is because it's an injective property. It has the injective property. So what it does is it can map any size tuple to a single number. The reason this is important is because we want to show that this size of infinity is equal to this size of infinity. And this is all the natural numbers. So all the natural numbers are from 0 to infinity. And this is called Aleph null. Null, I don't know, something like that. Basically, it's all counting numbers. So if I can show that I can make anything like 2, 3, 5, and like 72 and 0, 0, 4 and 0, 4. Like if I can figure out a way to map all of these numbers to a distinct integer on the number line, then they are the same size infinity. And if they're the same size infinity, that means they're both countable. And that's the basis. So there's two types of infinities. There's infinite and countable. I'll just denote it like that. And then infinite and uncountable. Right. Infinite and uncountable is all the real numbers from 0 to infinity. So 0, 1, 2, 3, 4, 5, etc. And then an example of uncountable is all the real numbers between 0 and 1. Right. Because there's like 0, and then there's like 0.1, and then there's like 0.2, whatever. You can't count all of them is the point. So therefore, this size of infinity is bigger than this size of infinity. And if we can see that any infinity that we get, if it maps to this infinity, then it's countable. If it's not able to map to this, then it's automatically uncountable. And Godel numbering is a way to map any size set to the real number, to natural numbers. Okay. That's just the theory. And now for how to answer exam questions. The way Godel numbers work is you have a tuple and then they map to a real number. When you convert from tuple to number, you have to add one to the exponents. And then when you convert back, you have to subtract one from the exponents. So what do I mean by exponents? We're using prime factorizations to represent every number. So any tuple, like for example, this one, 302. This represents the number of twos. This represents the number of threes, and then this represents the number of fives. Because this is the first prime, this is the second prime, this is the third prime. And what we're going to do is we're going to take these numbers, we'll treat these as the exponents, and then the position represents the what prime it's for, right? So this is 2 to the 4th, this is 3 to the 1st, and this is 5 to the 3rd. How did we get this? We added 1 to the exponents. These are our values for the exponents, and we know the bases because of the positions that the numbers were in. And then you just multiply this out, and then you get 6,000. You're not allowed a calculator on the exams. The best way to do this is to take the 2s and the 5s, multiply them as many times as you can. So there's 3 in common, so that means that's 1,000. And then all you're left with is a 2 and then a 3, which gives you 6, and then 6 times 1,000 is 6,000. So it's pretty simple. Are there any questions? Where are people putting questions if they have? Let's use that.
Do you want us to unmute or just use the stream chat?
Either, but let's use the room chat if people can't unmute. Okay.
Can you show us where you got those numbers again? The 2, 3, and 5?
These are prime numbers,
Right.
right? And the position of the number represents what prime. So this is the first position, so it represents the first prime. Second position represents the second prime, and third position represents the third prime. You're not allowed to skip primes, which is important, because if I take a number like 10, 10 is not a Godel number. The reason is because when you break it down into its prime factorizations, you get 2 and 5. But in order for a sequence to exist in Godel, it has to have all consecutive primes in it, right? So I can put like numbers for the 2 position, and I can put numbers for the 5 position, but because I don't have any 3s, that's a problem. And how would I even put the numbers in? Well, I see that this is 2 to the 1 and 5 to the 1. So when I'm going from number to sequence, I subtract 1 from the exponents. And so I'll get 0 and 0, but then I don't have a number for here. And then you might say, why not -1? Well, -1 is not a natural number, right? We're only dealing with numbers between 0 and infinity, which means we can't use negative numbers. So therefore, you can't represent 10 as a Godel sequence.
Time is it? No, what time are we doing?
Are there any questions? Can you show how you did the multiplication again? So you're not allowed a calculator on the exam. So the easiest way to do this is to multiply the 2s and the 5s, so you get 10s, and 10s are easy to multiply, right? So if you have something like, so there are 3 5s and then there are 4 2s, but there's 3 in common. So I could do like 2 times 5, 2 times 5, and 2 times 5, right? Because this is easy to multiply, this is just 1,000. And then I just check, oh, what else do I have left? Well, I have 1 2 left, and then 1 3 left, which is 6. And so then this is just equal to 6,000. It's just the easiest way to do this. Otherwise, numbers can get pretty annoying. For example, try doing 501. Well, no, I've seen bigger number, like bigger Godel numbers on the exam before. But yeah, basically, you don't have a calculator, so you just gotta figure it out. Figure out the easiest way to do it, and you will lose points if you multiply it wrong. So you'll get that part wrong. So don't. Okay. So this is just a simple going back and forth. So let's do an example where we actually do get we have a Godel number. So let's do 2,940, right? Just by cheating, I know that there is an answer, but I'll show you how you can get to that answer easily without having to need to do that, use a calculator. So 2940. So I see that there's a 0 at the end. So immediately I know that this has 2 and a 5 in it. Right. And remember, I'm not allowed to skip primes. So now 294 and times 10, right? Times 2 times 5. Right. And then 294 is even. So let me just pull out another 2. And then I get like whatever 294 divided by 2 is. Fuck. Okay, let's go back to long division. So that's a 1, that's a 4, it's a 7. So we get 147. So 2 and 147. But what the hell is a factor of 147? I don't know. But what I do know is that I can't skip 3, right? So if there doesn't exist a 3 in 147, then I can just stop. This is not a Godel number. And then I don't have to figure out what the sequence is. But let me just do 3 divided by 147. See if that gives me anything. The way to the trick is just add up all the digits. If it's a multiple of 3, then it is divisible by 3. So 1 plus 7 is 8, 8 plus 4 is 12, 12 is divisible by 3, so this will give us an answer. So 3 divided by 14 is 4, then minus 12, and then you get 27, 27 is 9. Okay, so this breaks down into 3 and 9. 27? 49, I mean, sorry. Okay, so 49 is easy. If you know your perfect squares, this is a 7 and 7. Okay, cool. So I have I have 2 2s. So 2 squared. I have 1 3. So 3. I have 1 5. So 5. And then I have 2 7s. Okay. And then from here, I just follow the rule. This is from number to sequence, which means I subtract 1. Okay, so I have a 2. So that means the first number is a 1. I have a 1, so the second number is a 0. The next number is a 0. The next number is a 1, and that's our answer. Any questions with that? Could you walk through this?
Question.
Oh, sorry.
You go ahead.
Could you walk through the steps again, if possible? Like, what are we trying to calculate towards? Okay. Let me answer your question, and then I'll go back to this one. What were we gonna ask?
I was going to ask for the previous question. Why are you adding 1 to the exponent?
That's the rule. Remember this rule. At one point I did explain what's the point of the rule, but if you don't need to know what the point of the rule is. If you just memorize the rule, that works. The reason for the rule is we don't allow negative numbers, right? And we don't allow skipping. So that way, if like 3 didn't exist and we didn't subtract, then we would allow 0 in a sequence, right? So let's just take 10 as an example. What would the sequence if we didn't subtract? We would get 1, 0, 1. But we don't allow not skipping a prime number. So therefore, we don't know that we skipped the number here because it's 0, but we can allow zeros because 0 is a natural number. So by subtracting 1 from everything, we get 0, -1, and 0. And now we know we don't have a natural number, which means this doesn't fit the pattern. That might have not have been the best way to explain it, but just memorize the rule. That's all you need to absolutely know. Where did you learn those number tricks? I don't know, I'm a nerd. Mathletes, I don't know. I'll show you more number tricks if they pop up. But let me go back to the original question as to what are we calculating towards. When you're given an integer and you're asked to calculate the sequence, you need to figure out its prime factorizations. From the prime factorizations, you can create the sequence if it doesn't skip any primes. Right? So that's what we're calculating, trying to figure out the prime factorization. From 2,940, we got the prime factorization right here. And then from here, putting it into a sequence is just as simple as subtracting from the exponents. Seeing that we didn't skip any primes and then just subtracting 1 from the exponents to get the answer. Does that answer your question?
Kind of. So like if you're given like, for example, like 6, you have to figure out like the sequence of the numbers by finding out what primes add to 6. Or
No, not add,
that's
multiply.
how-
Prime factorization is multiplication.
So you multiply the primes towards like that add to 6.
Why do you say add? You multiply to 6.
Okay.
Right? What is the prime
Otherwise,
factorization of 6? Just 2 and 3.
Yeah.
So 2 to the 1, 3 to the 1, which means our sequence is 0, 0.
And that's valid, correct? Because there's no negatives, right?
Yeah.
Okay. Thanks.
Cool. Let's do a couple more of these and then we'll move on to the ones with letters. So let's real quick do this one. So let's okay, let's write down the rule. Excuse me. All right, sequence to number. We subtract 1, or we add 1 to the exponent. And then when we go back, we subtract 1 to the exponent. Okay, so now we have a sequence, 5, 0, 1. And now we add 1 to the exponent. So this we get 2 to the 6, because this is the first prime. This is the second prime, so 3 to the 1. This is the third prime. So 5 to the second. Okay, so how do we multiply this out? Well, there is 2 5s here and 2 5s here. So let's just 2 2s here. So let's just put those together to get 100. So now all that we're left with is 3 times 2 to the 4th. There's no easy way to multiply this other than just multiplying it. 2 to the 4th is just count 2, 4, 8, 16. So this is 16 times 3. And then 16 times 3 is 48.
Yeah.
Okay.
6 times 3 is 18, carry over to 1, 3 times 1 is 3, plus 1 is 4.
Thanks. You're faster than me. Okay, cool. So now we have 48. And then 48 times 100 is just 480.
But you're smarter than me. so-
I don't think so. You can also break it down into 3 times 4 times 4. Where did the 2 to the 5 come from? There is no 2 to the 5. Yeah, okay. So like yeah, whatever way helps you multiply it out and get to the right answer. Yeah, just do that. There wasn't really any tricks to multiplying this. I don't know, 3 times 4 times 4. Is this simpler? 12 times 4. 12 times 4 is simple, actually. That's obvious. Okay, so 12 times 4 is 48. That's pretty easy. Where did the 2 to the 6 come from? Sorry. The sequence, the rule. It's a sequence to a number, so you just add 1 to the exponent. Is there ever a case where the image does not exist? Yeah. We'll get there. Any other questions?
So finding these numbers is literally just writing writing prime numbers and not making sure to skip any. And
Yeah.
then putting the sequence as the exponents for each of them plus 1. And then that's it. We just multiply.
Repeat.
Okay, I might not have.
So are you going from number to sequence or sequence to number? Because you said +1, and I thought you were going from number to sequence, which means you would do
I mean
minus 1.
like plus 1 in the exponent.
Right. So it's +1 in the exponent when you're going from sequence to number, and then -1 when you're going from number to sequence. It's important to know that, like, get that right. So yeah. Cool.
Okay.
How would we prove an image doesn't exist for a test if it's showing that there aren't consecutive primes? Yeah, just show that you skip a prime. We'll do that. We'll do a question. No calc on test. Yeah, there was okay. So let's do one where we don't let's do one more where we're converting it, and then let's do one where it doesn't work. And then how we prove that. Okay, so 2, 7. Let's write the rule down. So going from sequence to number is +1 in the exponent, and then it's -1 in the exponent. So we're going from number to sequence, so -1, but we need to first get the prime factorization. So 2, 7, 3, 0. There's a 0 here. So that means this is a 2 and a 5, and then 7, 3. This isn't even. I don't know what numbers divide into it, but I know that it needs to not skip. So let me check, does 3 work? 7 plus 3 is 10, 10 plus 2 is 12. So this is divisible by 3. So we get 3 divided by 2, 7, 3. 3 divided by 27 is 9. And then there's a 1, 91. So this is now 3 and 91. Okay, how do we divide 91? The fuck? What even? So it's not divisible by 2, it's not divisible by 3. So we know it's not divisible by 3 because 9 plus 1 is 10. And 10 is not divisible by 3. So it's not divisible by 5, doesn't end in a 5 or a 0. And so now let's check 7. So 7 divided by 91. Right, we're working up because we don't want to skip anything, right? Okay, so this is 1 minus 7, so get 21. 9 times this is 3, 13. Okay, so this breaks down to 7 and 13. Yeah, nice. Yeah, 13. Okay, so the next prime we get after this is 13, but 11 is a prime, which means we skipped a prime number. So this doesn't exist. Right, so you see here, her proof is 2 times 3 times 5 times 7 times 13. Misses 11, not a Godel number. No pre-image, whatever. Just say it skips 11. So skips 11. 9 is not a prime. Damn, everyone's roasting you, bro. Yeah, 9's a perfect square. Cool. So that was an example where we didn't have an image. And that's how you write the proof. You just say it skips that prime. So yeah, know the first couple of primes. It's worth going up to so it's like 2, 3, 5, 7, 11, 13, 17, and 19. and then 23. When we go 2, 5, isn't that skipping? Well, it's the 3 is somewhere. We didn't get there yet, right? The fact that it exists somewhere, like we're skipping it in our work, but like I mean, we're not skipping it, is what I meant to say. Like here, there doesn't exist an 11, so it skips 11 in the sequence, is what I mean. Yeah. Okay, these are like all the prime numbers I could think off the top of my head in order, but you do need to know quite a couple. Like if you look at some of these questions here, if you need to know the first 6 prime numbers in order to answer this question. You know, there's a 0 of the last digit. What happens if the last digit is odd? So you're saying like, what if she asks you something like 327? So think about it. If the last digit is odd, this is not an even number, right? If it's not an even number, that means it's missing 2. Where did 2, 5 come from? And so if this is confusing you guys, just the goal is to get the prime factorization from this. However you get it is all that matters. I'm just doing this trick because that way I don't have to deal with figuring out the prime factorization of a 4-digit number versus a 3-digit number. 3-digit number is a lot easier. So we're given an uneven number, an odd number. It's not a Godel number from the base. Yeah, exactly. All Godel numbers are even by definition because it needs to include primes. And the first prime is 2, and you can't skip primes, which means it has to have at least a 2. Okay. Let's continue. Let's skip over to where we have variables and stuff. Okay, so let's do this question. So now this question is a little bit harder. It shows now understanding of the application of Godels rather than just following the rules. So again, the rule is +1 for going from sequence to number and -1 going from number to sequence. So let M be the image of the sequence. All that means is M is the number that this sequence represents. Find the pre-image of 78M. So what that means is figure out a way to have a Godel sequence for 78M. But notice we don't know what M is, except for that it's this integer, it's this sequence here. So the way we're going to do this, and this is going to get a little bit complicated, we're going to put numbers in the sequence. We're going to start with this because this is the M part, and then figure out what 78's primes are, and figure out how to put those in the sequence, right? So let me just do it and then explain it after. So we have 78. Well, let's break down 78 into its primes. So 78 is even, so that means it's 2 and it's divisible by 6. So the way you know it's divisible by 6 is because the digits add up to 15. 7 plus 8 is 15, and 15 is divisible by 3, and it's even, which means it fits the pattern for 2 and 3. So let's just take out 6. You can combine rules, right? 6 is not a prime number, so it doesn't have its own rule. That way, 6 divided by 78 is 63, 18. So 13. Right, just do it out. Let me the way I did it in my head was minus 60. So that means this is 10. There's 10, and then you get 18. And then 6 divided by 18 is 3. So that means 78 divided by 6 is 13. Okay, and then this is just 2 and 3. And the sequence we have originally is x1, x2, x3, x4, x5, x6. Okay, so we have prime numbers that already exist in this sequence, right? These have to be valid numbers. But now we need to figure out how can we fit in another 2, how can we fit in another 3, and how can we fit in another 13, right? If all of this is equal to m, and we want to represent 78m, well, that means just take whatever this number was, multiply it by a 2, a 6, and a 13. Okay, so where does 2 go? It goes into the first spot, right? Because the first spot is for the first prime. 2 is the first prime. So how do we put 2 inside this? All we do is we say that, hey, well, if m has x1 number of 2's, that means 78m has x1 plus 1 number of 2's, right? However many 2's existed in m are over here. And then and then we know that there's only one extra 2 in 78. So let's just put it into the sequence. And then we get x1 plus 1. Does this make sense? All we did was figure out a way to put the 2 into the sequence. Cool. This is we'll do a couple of these and then, right? So oh shit, this is not a 3. This is I mean, this is not a 6, it's 3. Where does 3 go? 3 is in the second position. So that means in order for it to be x, in order for us to fit it, it needs to be x2 plus 1. And then where does 13 go? 13 is the 6th prime number. So that means it needs to go here. Right? 2, 3, 5, 7, 11, 13. Yeah. Okay, so we didn't touch x3. We didn't touch x4. And we didn't touch x5. But we know x6 needs another 13 in it. So that means we need to add 1. And so this is our answer. Questions? Nice. I've lost all of you guys. I'll clarify, don't worry. Why you kept x5, comma x6, oh, that's x4. Sequence exists. Okay, here. I think the reason it's confusing is because we just jumped straight into the variables. We never touched any of these, right? What does x3 represent? It represents the number of 5s. Are there any 5s? No. Are there any 7s? No. Are there any 11s? No. So that way x3, x4, x5 don't need to be changed. Let's say there is 2 2's instead of 1, then it would be, yeah, exactly. Let's use real numbers real quick and then and then go from there. So let's say we wanted to do, let's say m was let's make a much smaller example to mess with. Okay, so say our m was let's say it was 60. Right? So what's the Godel sequence of m of 60? It's 0, 0, 0. Right? My bad. Let me not skip everything. All right, what's the prime factorization? It's 2 times 3 times 5. Right? We saw that there's a 0. Oh no, so that's it's 2 times 5 in order to get the 0 away, and then we have 6 here. Right, and then this is 2 and 3. So the prime factorization of, so it's 2 to the 2 times 3 to the 1 times 5 to the 1. Okay, so that means my sequence is 1, 0, 0. Cool. I took it my 60 and I turned it into a sequence. But now what if I wanted to do, did someone say anything?
Why is it 2 squared?
6. There's a 2 here and there's a 2 here.
Oh shit. Okay, thanks.
So now let's say I wanted to do right, I called it M. So this is now my sequence for M. Right, but now what if I wanted to do 6M? Right. What I'm doing is I'm taking whatever prime numbers are in M, in 6, and I'm just gonna add them to the sequence. All right, so what's 6 prime factorization? It's just 2 and a 3. So now let's figure out a way to put 2 and a 3 in, right? 2 goes here, and then the 3 goes here. So that means our new sequence is now 2, 1, 0. And did this work? Let's figure it out, right? So what's 6 times 60? 360. What's the prime factorization of 360? Well, it's there's a 0 here, so that means it's 2, 5, and then what? Yeah, and then 36 is just 6 squared. So that means this is just 2, so 6 and 6. So this is just 2, 3. This is just 2, 3. Right? So then our prime factorization is 2 to the 3rd times 3 squared times 5. How do we turn this into a sequence? Well, you just subtract 1 from the exponents. So we get 2, 1, 0. And they're the same. So what did we do? We just took M, which already was a sequence, and then just put 6 into it, right? So just figured out a way to put 2 and the 3 in. That's basically what's happening here. M is a number, and this is the sequence for the number, but we want to do 78M. So all we're doing is introducing another 2, another 3, and another 13. So where does 2, 3, and 13 go? It goes in the first position, the second position, and the 6th position. And therefore, this is the answer. Does that clarify things for people?
Yeah, sort of. It did. Thanks. It helped.
Nice. So let's go to E, part E. So in part E, it says, let n be the image of the sequence x1, x2, x3, x4. Under the image represents the under the Godel numbering represent the image of the sequence this. So now we're doing the opposite. We're taking numbers out, right? We want to represent this as some function of n. So the way you do that is you just have to pull everything out. We pull all the numbers out. And how do we do that? So let's start with this. So x1 plus 2, x2 plus 1, x3, x4, and then 1. And our goal is to make this look like this. x1, x2, x3, and x4. Right. So this first position doesn't look like this first position. The reason they're different is because this has 2 more 2s. So in order for these to look the same, I'll need to bring 2 squared outside. I need to get rid of this plus 2. And so by getting rid of it, I'm just moving it out of the sequence. So if I have the x squared on the outside, then this part is gone. And now this spot and this spot look the same. So let's continue doing that to get all of the spots looking the same. This doesn't look the same as this. This has a +1. So how do I get rid of this +1? That means I need to bring out 3. Bring out a 3. That way there's one less 3 in the sequence. And now the spots look the same. X3 and X3 look the same, so they're good. I don't have to pull out anything from the 5s. X4 look the same, so I don't have to pull out anything from the 7s. But notice there's a spot here and there's no spot here. So in order to completely get rid of this position, I need to follow the rule where I did +1 to the exponents. The reason I didn't do it here is because there still exists prime numbers here in all of these positions, so I don't have to follow the rule. But because I'm trying to completely get rid of this spot, I need to remove all the prime numbers, which means that I have to do the +1 rule. So this is in the 5th spot, which means it's the 5th prime, so that's 11. 11 squared in order to completely get rid of this spot. And now in my first spot, I have x1, x2, x3, x4, and then that's it. I don't have another spot here. I completely got rid of it, which means these two things now look the same. And I can represent this thing as n. So now all of this is now n. And now I need to figure out how to multiply this. This is kind of fucked. 11 squared is 121. And then this is 4 times 3, which is 12. And then let's just do 12. 2, 4.
Let's say recording. I think this is recording.
Yeah, I'm recording. And then 1, 2, 1, 2, 5, 4, 1. So the answer is 1,452 n. Right? Are there any questions on that?
Could you go over how you got 11/2?
Yeah. Wait, 11/2?
Like I got the 11 part, but wouldn't it be 1?
The 11 squared?
Yeah, my bad.
Oh,
Sorry.
because originally over here there was a 1, right? And we're trying to completely get rid of the spot, which means we need to follow the rule. The rule is +1 to the exponent.
Oh, okay, got it. Thank you.
Right. We didn't follow the rule for any of these because their spots still exist. And so therefore, we didn't need to do the +1 rule, but because we do it, we get 11 squared. So now this is gone.
I still don't get the 11 part.
Okay, let's go back to the rule and let me just do an example. A very simple example, but let me do it slowly so like you have a better understanding what this rule actually like implies. Right? If I'm going from 2, like say the sequence I have is 2, 3. What I'm like, let's work backwards and then let's pull things out of the sequence to get what the integer, what this maps to, what number this maps to. So this 3 here is in the 2nd position, which means it's 3 to the 4th power. This is too big of a number. Let me make this number smaller. Let's do a 1 here. I'm not that smart. We can put a 3 here. Okay. Right. This is in the 2nd position, so this is the 3rd, this is 3, and there's a 1 here. Right. So this sequence here, this 3, 1 is equivalent to 3 squared times 3. Does this part make sense? All I did was take this number out move it outside, and follow the rule.
Where did that? Where did that 3 come from? Like the last 3, the one in the brackets you just put.
It's right here. It's this 3 here.
Why is it not?
There's a 3 here, no?
Yeah.
Right. So this is, so all I'm saying is this 3 is in the first position. I made up this example, right? This 3 is in the first position, and this 3 is also in the first position, right? I haven't touched this number yet, but in terms of the second position number, I moved it outside. Does that make sense?
Oh. So it's not.
By moving it outside, it looks like this now.
Yeah.
Okay, and then how do I get rid of this number, this 3 here? How do I move this outside? That means this is equal to 3 squared times 2 to the 4th. Right? And then whatever this multiplies out to, like 8 times 9. Oh no, 16 times 9. What the fuck did I do these numbers for?
So can I ask a question? So which one created 3 squared and which one became 2 to the 4?
Sorry, what?
So from what we were describing, which of the numbers in the sequence between 3 and 1 became 3 squared, and which one ended up equating to 2 to the 4?
This is in the second position, so this has to be for 3. This is in the first position, so this has to be for 2.
Okay.
Right? The positions represent the prime numbers. So if there's a 3 here, that means it's for the second position number. There's a 2 here, that's for the first position number. These represent the prime numbers.
So technically, it doesn't matter what order since we're just multiplying.
Yeah, exactly. We're just multiplying.
Switch over first.
Should it be 2 to the upper 2? Or is it 2 to
Shouldn't this be 2 to the should it be what?
2 to the 2, right?
But there's a 3 here. When I'm going from sequence to number, I add 1.
Oh, okay, got it.
Cool. So the reason I did this side example is because there's a difference between manipulating the position and completely getting rid of the position. What we're doing in what we did in like the x1, the x2, is we just changed what the number that was there, but there still exists a number there. Until we've completely removed the number like we did here, then we don't have to apply, then we apply the rule. Otherwise, we don't apply the rule, this rule here. All right, so just take the number, if we're taking the number out, then we apply the rule. That's why this is an 11 squared, whereas all of these aren't, don't have +1 to the exponents. Cool, is everyone good with that, or do we want to do one more example?
I'd appreciate if we did one more.
Okay. Yeah, the last number was 4, then it would be 11 to the 5. Just kind of a fucked up thing. 11 to the 5 is if you can't multiply in your head, it's 1, 2, 3, 4, 5, 4, 3, 2, 1. No, I lied. I'm fucking retarded. Yeah, that looked way too big of a number. There is like a pattern with like multiplying numbers. 11s. I don't even know how to multiply 11 to the 5th power. She typically gives you numbers that are manageable without a calculator. So let's do one more example, and then we're gonna move on to the next topic. So let's do this one here. Right, so we're given a sequence and we want to convert it, we want to factor everything out. Wait, this is what we just did. No, we didn't do this one. This is a new one. Okay. So let's move all the numbers out. X1 plus 1, X2, X3 plus 1, X4, 2. So we have a +1 here, and we want it to make it look like X1, X2, X3, and X4. All right, so do we not subtract or add exponent? Oh, sorry, what was this question? Fuck, what was the previous example? I stopped paying attention to the chat because there was like side conversations happening.
It says 11 to the power 1 plus 1 is 11 squared 2. I mean, 11 squared.
We're going from sequence to number, so we do +1 to the exponents. I think sequence to number would be adding 1, exponents to numbers in sequence, adding 1 to the exponent number. Yeah, so that we're going from sequence to number, so +1. That's why we're adding it. Let's move on to the next example because I'll cover this again. Both a different question. Okay, so this question. I was talking about the letters. Cool. Can I do this question and then and then you ask it here? Because this is just the same type of question. Okay. So there's a +1 here, right? I want to get rid of this +1. That way this first position looks like X1. How do I do that? I put 2 to the first power on the outside. I'm just getting rid of 1, 2. These look the same, so they're good. This has an extra 5, so I'm going to move this outside, right? This has one more 5 than this does, so that's why there's an x to the 5. There's a 5 to the 1 on the outside. And now we can change this. We can get rid of this. This x4 and this x4 are the same. And then this 2 over here is the 5th prime number. 5th is 11 still. And so we now have an 11 to the 3 on the outside in order to completely get rid of this position, right? We apply the rule because we're completely removing this position, this spot here, right? We didn't completely remove any of the other spots, so we never applied the +1 rule to any of them. So now we have this, all that's left in the sequence is x1, x2, x3, x4. This is all equal to n. So now we just need to figure out how to multiply this out. This is just 21 times 11 is this is 1331. And then so 13310. There'd be a question where you have to add a spot. Yeah. It's probably the next example. No, she didn't give it, but
So at the end, you have to multiply the entire like number out to. Or do you just leave the sequence?
This is the answer.
So it has to be a number, correct?
Yeah,
Okay.
you're representing it in terms of n. That's why there's no sequence. Did your question come up while going through this example? No. The Bob Blue dot blue.
Is there a link or a file for this test or?
I can link everything.
Alright, thanks.
Okay. Cool. Let me do an example. Since it didn't pop up on any of these, let me just make an example where you would have to add another position and then what that does. So going from like let's do 13. No, let's do 23M. No, wait. What's the prime after 13? It's 17, right? Yeah, okay, let's do 17M. So let's do this question here, but 17M rather than 143M. And then I'll show you what's different. Right. Okay. So in this question, we're given a sequence, this x1 to x6. And we need to figure out, and this all represents M. Whatever integer M was, its Godel sequence is this. But now we want to figure out a way to represent 17M. Let's make this slightly more difficult. 17 times 2 is 34. Let's make this 34M. Right. So we need to break down 34 into its prime factorization. Well, 34 just breaks down into 2 and 17. And now we need to figure out where do we put 2 and 17 in our sequence. So we have x1, which represents the 2's. We need to put one more 2 in it. So this first position is now x1 plus 1. x2 represents the number of 3's. And we don't have any 3's. So we keep those the same. x3 represents 5. We don't have any 5's. We keep that the same. Same thing with x4 and x5 and x6, right? Because this represents 2's, this is 3's, this is 5's, this is 7, this is 11, and this is 13. Yeah, exactly. No reply. I don't even know what your name is. Yeah, the answer is, yeah, you do add a 0. Right, but now we need to figure out a way to make space for the 17. Right. But it can't go in, and it doesn't go in any of these. It needs to go into the 7th position. But there is no 7th position. But we can add one by making space for it. And then if we do, we need to follow the rule of subtracting 1 from the exponent. Right, we're going from number to sequence, so that's a -1. Right, so how do we put the 17 in? We make a new spot for it. We make a new spot for it. And then we do the -1 to the rule, to the exponent. So it has a 17 to the 1 exponent, which means that there is now a 0 here. So now this is our answer for this example. We figured out where to put this to, and then we figured out a way to make space for the 17. In a question where it said something like, oh, prove that this representation doesn't exist, that would be an example like, let's say it said 23 is 20, yeah, right. If this was 23M, the prime after 17 is 19. 19, okay. But in M, we only go up to 13, which means we would need to figure out a way to make space for a 17 and a 19 in order for us to then have the 23 that we need. But there aren't any 17s or 19s. Right? So if there are no 17s and 19s, it's impossible for me to put in 23. The fact that everything up until 17 already existed made it possible for me to add 17. But because I'm missing 17 and 19, then I can't add 23. Therefore, if I was asked to write the representation of 23M, this would be it doesn't exist because it's missing 17 and 19. Okay. Cool. We're gonna have to move on to the next topic. But any questions? Cool.
Yes, one question. So what do you put if it doesn't exist? Do you have to write out the whole, do you just write like the solution and then say you can't add the two numbers, or?
You just need to prove it. All you have to do is write something like this, misses 11. So this example misses 17 and 19. That's it.
Okay.
So let's move on to regular expressions. Let's do this. Okay. I was just gonna go until I covered all the topics. Unless you guys have an objection. You guys have a bedtime or something. Okay. So in regular expressions, there are only a couple of symbols, right? There are parentheses, there is a star, there is union, and then there's anything in your alphabet, right? So let's start with the alphabet. Your alphabet will always be given to you, right? So in this example here, it says, it'd be strings over the alphabet ABC. So in this example, sigma is ABC, right? So the only symbols for any of these regular expressions are parentheses, stars, union, and then anything in your alphabet, and also lambda. But lambda just represents nothing. It's empty string. So this isn't used that as often, but it exists. These are all the symbols. And concatenation. Well, there's no symbol for concatenation, but yeah, we also concatenate. We are making these rules to create strings and which require concatenation. Sigma is always the alphabet. Yeah. Okay. So the way you create strings is by concatenation, right? You take anything in your alphabet and based off of the rules that we're applying here, you'll generate strings. So for example, if I said something like A or B, right? This would represent A or B. But then if I did something like C, A or B, the strings I get are CA, CB. These are the possible outcomes. So the parentheses are here for like grouping them. And then union is your options. So either the left side or the right side. And then star, right? So we know that star represents 0 to infinity. And so this represents repeating the instructions as many times as necessary or as many times possible. So if I had something like A star, this would mean repeat writing A any number of times. So I could get A, or I could get AA, or A, keep going. It's like an exponent, yeah, which tells you how many. Exactly, it's countably infinite. Remember, countably infinite also includes 0. So what if I did this operation 0 times? I don't get any A's, which is equivalent to lambda. Right? So Oh shit, we didn't do those cardinality questions. Okay, after this, we'll go back. I'm thinking this example, there's also some cardinality, but we'll go back to countably infinite, things like that. If A star is equal to 0, the same thing as lambda. Yeah, exactly. If the star is equal to 0, then A star is lambda. Yeah. So yeah, it's just repeating the operation as many times as necessary, or as many times as it wants, anywhere between 0 and infinity times. Right? So A or B star gives you any combination of A's or B's. Right? So BA, AB, BB, AAA, right? All of these exist here because at any given time, no matter what this variable, the star represents, it'll be an integer. And then in each, that's how many times I repeat this operation, which says either pick an A or a B. So A or B star represents any combination of A's or B's. And if my alphabet is ABC, my alphabet is ABC, then A or B or C star represents any string possible in our regular in our language. This represents every possible string given our alphabet. Does it make sense? There's an infinite number of combinations for A or B star, right? The star represents infinity or an infinite number. No, I I got COVID. That's why I'm coughing. But yeah. But does this make sense why this represents everything in the alphabet? This is a very important concept because when we are creating our regular expressions, we sometimes need to think, can anything be there? And if we say anything can be there, then we will use something like this. Yeah, it's because at any point in time, so let me do an example. So like, let's say the star was equal to 2, right? Then I would get A or B or C, A or B or C, right? The reason being, I took this operation and I repeated it twice. So star equals 2. I repeated it twice. So how many options do I have from here? So all possibilities. So there are 3 options here, 3 options here. So the 9 possible strings I can get is AB, is AA, AB, AC, BA, BB, BC, CA, CB, CC. Yeah, exactly. So AB could be AB, right? The way that happens is if this star is equal to 2, and then I get A or B, the first one chose an A and the second one chose a B. Therefore, I get the answer AB. Same thing here. We have 3 options, but notice there are no other possible 2-length strings in my alphabet. This is all the possible ones, given that I can only use A, B's, or C's. Which is why this A or B or C star, represents any possible string. Because now all I can do is just make this a 3 or 4 or 5 or any number, and it represents that many combinations of this A or B or C, which can take up any of the values in my alphabet. This is important to know. When we're building regular expressions, we're going to be asking ourselves, can anything go there? And you'll need to determine yes or no. And if yes, anything can go there, then yeah, exactly. So what if the star was equal to 0? Well, then you get lambda. And how many empty strings exist in any alphabet? Only 1, which is why the only possible string you get when star is equal to 0 is lambda. Let's aim for a break at, what is it, 7:30? Just like a 5-minute break. So let's start doing questions. So let's do these questions. Nah, it seems pointless to take a break after I just explained this without doing any examples. So let's do these examples. So this one says write a regular expression that represents L1. So what is L1? It says let L1 be exactly those strings over the alphabet ABC whose length is not greater than 3. Is A star and A lambda the same thing? No, not even close. Right? A star and A or lambda means I can get A or lambda. Right? Whereas this I could get A or AA or AAA or lambda or any number of A's. So no, they're not the same. This is finite also. This is infinite. You could tell it's infinite because it has a star. And this doesn't have a star. Without a star, it can't possibly be infinite. All right. So let's do this example. So it says whose length is no greater than 3, right? So that means we can have a length of 0, a length of 1, or a length of 2. How do we get a length of 0? Well, that's just lambda. All right. How do we get a length of 1? Well, that's just either A or B or C. And how do we get a length of 2? Well, that's just A or B or C twice. So this is my answer. I mean, these are all the possible outcomes. But now how do I write this as a regular expression? Well, it could be 0, or it could be 1, or it could be 2. And so this is my answer. It's different from her answer, right? Her answer says, it reads like this. A or B or C. All right. So from here, you can't modify the value of the star. The star represents every integer. So you can't say something like A or B or C to the third power. This isn't a regular expression. We don't have numbers in a regular expression. All right, that wasn't one of the symbols we could use. So her answer here, it reads like this. Either pick an A, a B, or C, or nothing. Pick an A, B, or C, or nothing. Pick an A, B, or C, or nothing. If I pick an A, B, or C, then I'll from all of these, then I'll get a length of 3. Wait, this said no greater than 3. Whose length is not greater than 3. Oh, fuck. So that means that includes 3. Right, so we have to do this again. So we could do A or B or C. A or B or C. And then A or B or C. This is how I would have written my answer. But hers is, if I pick an A or B or C from any of these, then I get 3. If I pick a lambda from one of them, then I would get 2. Because if I say something like A lambda, this is equivalent to A. This lambda represents nothing. So when you concatenate lambda with anything, it's whatever that thing was that you concatenated it with. So A lambda is equal to lambda, is equal to A because the lambda is empty. And so she's saying here, if I ever picked a lambda for any of these, then the other two, then it would just drop it as a character. Right, so if I picked lambda and then A, this would just be equal to AA, which is of length 2. No, any solution that is correct, you'll get full credit for. I deliberately chose to write it differently from hers so you could see both ways.
So putting that lambda on the outside is the same exact thing as the way that she did it, where she put the lambdas on the inside.
So I'll explain. The way I generated my answer was fuck. The way I generated my answer is all the possible strings that are of length 0. There's only one that's possibly length 0. How do I get of length 1? These are all of length 1. These are all of length 2. And then these are all of length 3. Because I'll pick one character from here, one character from here, one character from here, get 3 characters. And then 2 characters from here, 1 character from here. And this says pick nothing. Which means it satisfies exactly what her language wants. But the way she writes it is pick any of these, and regardless, you'll get either of length 3 if you pick A, B, or C from all of them. But if at any point you pick 1 lambda, then it's of length 2. And if you pick 2 lambdas, it's of length 1. And if you pick 3 lambdas, it's of length 0. So they're both the same thing. Mine is much more verbose. However you get the right answer, it doesn't matter. You could write it however you want. I was just deliberately choosing 2 ways of like a different way rather than hers, so you could see both ways. They're both full credit. Yep. Let's move on to part B. So in part B, it says, write L2. So L2 says exactly those strings over the alphabet ABC, where the number of A's is not less than 2. Right, so not less than 2 means 2 or more. Right? So the only way to guarantee that I have 2 A's in my regular expression is to manually put 2 A's together, is to manually add 2 A's in my regular expression. So I'm going to put them together, put them 2 A's down, right? They don't need to be next to each other. And so now anything I add after it means it'll count for sorry. These 2 A's are the only constraint that this language needs, right? So anything else that I add to it may or may not be there, like doesn't have to be there, right? So these A's don't have to be next to each other. So can anything be in between them? Yeah. So we can write A or B or C star, right? Remember, this is our everything, right? Our anything regular expression. It also doesn't say that the A has to be in the beginning. So that means I can do another A or B or C star here. It also doesn't say that the A needs to be at the end, A or B or C star. And so this is my answer. I started with whatever was absolutely necessary. So 2 A's is absolutely necessary for my regular expression. And then from there, I just fill in the blanks. They don't have to be next to each other. So anything can come in between it. It doesn't have to start with an A, which means anything can come before it. And it doesn't have to end in an A. So anything can come after it. The reason our answer is slightly different than hers is because her answer says this, B or C star, A, B or C star, A or B or C star. The reason she doesn't include the A's here is because you don't actually need to. I only do it because then it makes it a lot easier to just can it just be A? No, right? Because what if I wanted something like B, A? If my regular expression is A is what you wrote, then you can't possibly get this this answer. But this satisfies the rule, right? As at no less than 2 A's. But notice her regular expression will also give you that. Say I had an example like A, right? This is a valid string. The reason this is a valid string is because it has at least 2 A's. And but where did these A's come from? This A, how do I know that this A like is this first A this one, or is it like, or did an A come from the star, right? There's a little bit of ambiguity. This part doesn't actually matter, even though there is ambiguity, it doesn't matter, right? This first A here, I know for a fact from her regular expression comes from here. This second A, I know for a fact comes from here because there's no possible way of getting another A anywhere else. And then this, any other A's that come after it come from here. But you don't really need to know this type of intuition, right? As long as my regular expression could generate this string, then I'm good. And this is a valid string. So the easiest way to teach it is figure out what's absolutely necessary, put them in, and then fill in the blanks. And then that's it. But you won't really get that from her answer. This is not as intuitive, in my opinion. But they're both correct. And then part C says, write a regular expression that represents L1 union L2. Right, we already wrote L1 in part 1. Right, we already wrote it here. And then we already wrote L2 in part B. So all you need to do is copy whatever you wrote for part A, put a union, and then copy whatever you wrote for part B. And then that's your answer. Yeah, it's literally just building up on top of like abstraction, right? So this L1, we've already defined out here. And then this L2 we've already defined here. So you just combine them together with the union because it's that union's right here. And then same thing here. So L1 concatenated with L1, you just write L1 twice. So it's if you have to write that twice, whatever regular expression I wrote, that'd be kind of annoying, but you would have to just write it twice, like she does here. So her answer, like this, she just copies twice over. Because you can't generate a string like BAA. The fact that you say A or B or C star A means it's starting with an A and ending with an A. So the only valid strings you'll get are of length 2, but starting and ending with A's, and things like this will get missed. Make sure to include. No, parentheses just are for clarification. It doesn't actually matter anything, right? Notice all of these are all in parentheses because they're clarifying that these unions are extended to this part here. So this will get you 1 character. This will get you 1 character. But here, if you did add parentheses, it still would be correct. You don't need parentheses, is what I'm saying also. So if it makes sense for you to put parentheses, put parentheses. It won't be wrong. All right, we're gonna take a break now. We'll come back at 4:30. Yeah. Yeah, my bad, 7:30 your time. No, I'm not in California. Sadly, I'm in Seattle.
Do you mind if I ask a question before you start again?
Sure.
So with the L1 and L2, so you just combine part A or part B?
Yeah.
Like I know I'm a restate. Yeah. Okay. Thanks.
What ultra wide? I don't know. Let me check. Nice. I've got the most expensive one that Amazon would pay for. Yeah, I do tutor the database class, but it's not free. Not the most expensive one. I said the most expensive one Amazon would pay for. And they're cheap. I think this was like $300. I have LG ultra wide. Let me just Oh fuck, it's already 4:33. I don't know if Brennick knows I do anything. This is the monitor that I have. How did you get I didn't I used to I used to take the exams for students, so I learned this pretty well. Yeah, people at work call me Mike Ross. We'll begin in like 2 minutes. What year did I graduate? Bachelor's, I graduated 2021 fall, it was spring. And then master's, I graduated fall 2021. Real Giga Chad, I did my master's in like one semester. Yeah. It's the same, and like this is theory. It's not going to change. Just the cutoff is kind of risky. Like I don't know when she stops. Like there are some like semesters where like she'll teach context free grammars with telescoping, other semesters where she doesn't. I've even seen like a pumping lemma question pop up in some semesters, but if that happens, you guys just got to take the L. I don't know. I'm not doing that till exam two. um what Yeah, I do have that issue. I don't know how do I just deal with that issue, the scaling issue. I just deal with it. Is doing your master's worth it? Honestly, my recommendation is for other students is this market is so tough right now that if you can afford to do your master's and like not have to find a job immediately and settle for like a really shit tech job, you should do your master's. I don't recommend a master's normally, but like given the circumstances, master's is probably like I've seen Google like FANG companies, they're like preferred uh quality like qualifications is like masters and PhDs and things like that. Like that's a preferred thing and then like an entry position, which is kind of fucked. But you definitely don't need to. Um most of my friends are a lot smarter than me. They don't even have their masters. Um Math shortcuts are pretty good for problem solving. So if you get really good at problem solving, um that's kind of like how I managed to land a FANG job. Problem solving is like a pretty big skill that I have. Even just doing little math tricks like that is like an extension of problem solving. I'm not covering pumping lemma. It's a proof. If you guys are interested. Basically, we have to prove that any language that she gives you follows this rule. There is a template that I write that is so much simpler than whatever the fuck this means. But if this actually is like, I understand what this means. You don't need to understand what this means.
Can you zoom in if possible?
Yeah, have fun. I don't know. When did I enroll? To what? I was in the accelerated BAMA program. So I enrolled in that end of sophomore year. I don't I don't actually give a shit about the degree. Like, is master's at QC good? It's kind of like I just wanted the degree. I didn't want to spend a lot. I didn't like nothing from school I apply at work. Was I an international student? Yeah, I commuted from Queens. I like born and raised in Queens, and I commuted to Queens. I'm as international as it gets. I fucking hate international students though. They're so annoying. The market is just flooded with engineers right now, and a lot of them aren't. A lot of companies just aren't hiring. They're like hunkering down for a recession, so it's pretty fucked right now. But they're still there. Like in terms of like the percentages of companies that are hiring, they're there. you just probably won't be getting like really, really high, like tier 1 salaries, which honestly, even just getting like a 110, like 6 figures, like 110 is really good.
I have a question. Would you work as a professor in QC for the CS department? Like as a professor?
I'd be down. I'm trying to become a professor when I grow up. I want to be a professor.
They become a 320 professor, so no one can go through the two worst 320 professors. There's only like 2 options.
I would hate to teach 320. I would prefer to teach algorithms or data structures or some advanced class. 320 is such a garbage class. So many other colleges don't even teach this. Like I talk to people. What?
More messed up. You know, what's it called? JavaScript. There was like a mandatory JavaScript class I heard, and they got rid of it into an elective, like an optional elective. But like, I feel like they should have kept that instead of 320.
They're not removing 320 from the curriculum if that's their goal. Like regardless, it's a prerequisite to compilers, not compilers, principles of programming language. So there's very, very, very little that you need to know from this class for that class, which is why I don't even teach any of the theory to you guys. But I would teach at Queens too, but not theory of computation. I would stick to just telling people to watch the YouTube videos and don't go to class.
Well, I know a professor at like my old school at Farmingdale basically should have told us to watch his Udemy videos, and that literally like just like I watched it the summer before, and I had an A without even doing anything because I already knew everything.
Are you talking about 313?
Huh?
Are you talking about 313?
Different school.
Oh,
Yeah, I'm a master's student.
wait, you're doing this in your master's?
Huh?
You're
Yeah,
doing
I
this?
have, I have 2 conditional classes, like this one, and I think probably 241 math.
Wait, that's still. How'd you get to masters in? I thought you had to do.
My
that.
bad.
I
People
have-
are asking when we're starting, so we should start.
Oh,
And
That's just
yeah,
natural, that's all.
343 is a really gay class. I actually hate 343 so much. But it was kind of interesting. There are some interesting concepts. Shouldn't be mandatory though. So let's go on to a couple more. I'll come back to these. Actually, no, let me just do these since they're related to the ones that we're doing. So cardinality is listing the the size of a set, right? So we're asked here like how many what's the cardinality of L1? Right? How big is this? So either it's finite or infinite. If it's infinite, you need to figure out is it countable or uncountably infinite? And if it's finite, you need to figure out what that number is. And so that's what we're asked here. So right off the bat, F, G, and H, sorry, F and G, they're just asking for the cardinality of L1 star, and then this is L2. So L2, if you look back at the answer we wrote, has a star in it. If it has a star, it's immediately infinite and countable, right? So straight off, the answer for F is infinite and countable. L1 star that has a star in it, it's immediately infinite and countable. There's a star, it's infinite and countable. And now for E. So E is asking for the cardinality of this. But it's not, there's no star, which means it's not infinite and countable, which means it's finite. And now you need to figure out how many strings exist in this. It's a little bit difficult for you to immediately find it off of the reg expression she wrote. So let's go back to the reg expression I wrote. Right. So going based off of this, off the expression I wrote, how many strings exist in lambda? Well, lambda is an empty string, but there is exactly one empty string. How many strings can I get from this A or B or C? Well, I have three options, so 3 strings. How many can I get from A or B or C, A or B or C? There are 3 options here, and there are 3 options here, and they're concatenated. So when we multiply them, we get 9 possible options. It's like combinations, like in probability statistics class, right? I don't know, shirts, I don't know, and pants. How many outfits can you make? Type of thing. Okay. And then in this one, same thing, right? 3 options here, 3 options here, 3 options here, which means there are 27 possible strings from here. And then all we need to do is add these up. And then you get 40. Right? The reason you can't really do that with her expression here is because when you have 4 options here, it's because there's these lambdas. They make it a little bit difficult. I'm not gonna explain. It's just this is how you get the answer, and it's a little bit there's overlap between her thing here. And so you don't get the right answer just by multiplying over. But using the reg expression I wrote, you can easily get it by just multiplying and adding everything together. So infinite countable because there's a star, infinite countable because there's a star. And now it says the power set of L2. So this is where things are a little bit different. You can't just use this. The problem is there's overlaps between some things. For example, fine. For example, look at this, just looking at this. Right. Right. Say I picked a lambda from here, and then I picked an A here, and then I picked an A here. What string do I get? I get AA. Say I picked an A from here, and a lambda from here, and an A from here. What string do I get? I get AA. Say I picked an A from here, and an A from here, and a lambda from here. What string do I get? I get AA. There are multiple ways to get the same string, and because there are duplicates, you can't count that in your sets. Sets don't have duplicates in them. Which is why from her answer, it's difficult to get. You would need to figure it out based off of, you'd need to remove duplicates. And rather than actually do that, just do it the other way. But now for this part H here. There is a power set. So that P of X is equal to 2 to the X. Oh. My bad. There was a side conversation, so I skipped. She would accept your answer though, correct? Yeah, it's correct. The answer is correct. Like just because it's different. There's multiple ways to write the answer. But as long as they're correct, and then you get it. Nice. Okay, power set is 2 to the X of whatever is in the inside. Right? So if I'm said something like power set of 3, you just say it's 8. But the power set of anything infinite is infinite and uncountable. There was like a Cantor's theory or something that you might learn. The diagonalization proof, if that rings a bell. She covered it in class. Basically, the way you prove this is using Cantor's diagonalization proof. I'm not going to explain it to you. Just know that this is the outcome of knowing that proof. It's a pretty interesting proof, though, if you guys are interested. Not necessary, though. She did mention it. There's no way she didn't mention it. Okay, that's it. That's all you need to know. This is This is, just memorize this because here it says power set of L2. Right? So what is the cardinality of L2? Remember looking at L2, we see that there are stars, which means they were infinite. That means it's infinite. Doesn't matter what type of infinity, the power set of anything infinite is uncountable. Infinite and uncountable. Then therefore, that's why this is the answer. So let me go to a different exam because there are better regular expression questions to follow. And then, yeah, okay, these are a lot harder than the other exam. So let's do this one. I can talk more about that after the review. Let's just and maybe give you clarity on whether or not a master's is a good idea. But let's go over this question here. Right, so it says let L1 be exactly those strings over the alphabet A, B, C, G that satisfy all the following properties. The first symbol is a G, the second symbol is a C, and the length of the strings is even. Fuck. Okay. So the first symbol is a G. How do we make the first symbol a G? We just put a G down. How do we make the second symbol a C? Well, we already know where it goes. It goes right here. So we just put a C there. And then how do we always make it even? Right? How do you represent an even number? It's 2n, right? And this n can be any positive integer, right? Or a non-negative, any natural number, right? Which means this is kind of like 2 star, right? And then how do I get to any two characters? Well, this is just A or B or C or G. A or B or C or G, right? So then putting a star around this is just this. And so therefore this is always even. Does it make sense how I went from this to this? Because I'm going to do the same thing for odd. Okay, so now let's go do odd. How do I go make an odd number? Well, how do I represent an odd number? It's 2n plus 1. This part here we've already figured out. It's this thing here. So just A or B or C or G. Ignore my handwriting. I don't have a pen, I have a mouse. And then how do I get one more character at the end of it? I just add one more character. Right? So this will always be even, and then this is plus 1 character, so therefore this will always be odd. So even, odd, and so if this question said of odd length, you would have to modify the question to make it of odd length, right? But how do we know which one we need to apply to, which one we need to add to our string, right? This says the length of the string is even, but notice we have 2 characters here. So since I already have an even number of characters, in order to keep it even, I need to add an even number of characters. But for example, if there was like an A, like it said, A is the first character, G is the second character, C is the third character, and the string needs to always be even, then I can't just add like an even number of characters, right? I would need to do an odd number of characters plus an odd number of characters in order to make the whole string even. Does that make sense? So since we have even number of characters, we just take whatever we just add an even number of characters again to make the whole thing even. So we do that. And then a star. And that's it for the answer. We know nothing comes before it because G has to be the first thing, so we keep that blank. Nothing can come in between these because this needs to be the first and the second character, and then everything at the end of it is this part here. And so that's our answer. Okay, let's move on to the next one. Let L2 be exactly those strings over the alphabet A, B, C, G that satisfies the following properties. The first symbol is a C, and the last symbol is an A. The symbol G occurs at most twice. Okay. So what has to be there? C has to be in the beginning. A has to be at the end. And G occurs at most twice, which means G can occur 0 times, 1 time, or 2 times. So what we're going to do is we're going to say G, G. Right, so this is my 2 times. But if I wanted it to occur once, I would pick a lambda. And if I wanted it to occur 0 times, I would pick another lambda. So now this allows me to write 0, 1, or 2 Gs. Notice they don't have to be next to each other also. So we have a blank right here, and right here, and right here. We don't have blanks outside here or outside here because this is the first and last character. So what can go in between my C and the first occurrence of a G? Anything, as long as it's not a G. So close. We can't have more G's because if I have an A or B or C or G star, that means I could get G's from here. So this can only be A or B or C star. No, I thought I said at most. This is most to. If it was at least, then you'd be correct. Yeah. And then we wouldn't need the lambdas, but whatever. It says at most. Same thing here. Anything can come as long as it's not a G. And same thing here. And so therefore this is our answer. Cool. Okay, so let's move on to the next one. Let L3 be exactly those strings over the alphabet A, B, C, G that satisfy the following properties. The first symbol is different from the last symbol. The first symbol occurs exactly once. Okay, how do we know what the first symbol is? The answer is we don't unless we manually put it there. So we have 4 different scenarios. When the first symbol is an A, when the first symbol is a B, when the first symbol is a C, and then when the first symbol is a G. Now that we know what the first symbol is, now we can follow the rest. The first symbol is different from the last symbol. So what is the last symbol possible? What are all the possibilities for the last symbol? Well, it can be, if my first symbol is an A, that means I could have a B or a C or a G. If my first symbol is a B, what is my last symbol? An A, a C, or a G. If my first symbol is a C, my last symbol is a C, a B, or a G. And then if my first symbol is a G, then my last symbol is an A, or a B, or a C. And now we have these blanks here. So now we need to figure out what to fill in with these blanks. And we need to make sure that the first symbol occurs exactly once. Well, the first symbol occurring exactly once is already in the first symbol, which means I can never see another A. So all I have to do is just write anything other than an A. I don't know what that's supposed to mean. But I think you're on the right track. But so yeah, so this is just a B or a C or a G star. This is just an A or a C or a G star. This is just an A or a B or a G star. This is just an A or a B or a C star. And it could be any one of these. So all of these have unions next to it. And that's the answer. Does it make sense? Yeah, quick question. Yeah, you have to write all the scenarios. You have to be exhaustive to what the question is asking. Otherwise, it's not correct. You put a star because it represents all the possible ones, right? Otherwise, you would want. If I wanted one representation, I wouldn't need a star. You are putting a star. You are putting a star because you want to represent all the possible ones, right? Yes, the star represents all the possibilities. This is just necessary. So I think the question you guys are trying to get is, if this already means everything and this is the same, why don't I just combine them together? The answer is the star also means 0, right? So then if I combine them together, like say I didn't have this part here, then I could get a string that says A. But what's the problem with this? This doesn't satisfy the constraint that the last symbol is equal to the first symbol. Yeah. That's you gotta be aware of this. But yeah. I don't know if that exactly answered your question. I didn't kind of understand your question, but
Can I ask a question?
sure.
So I understand how, for example, like A is saying A and
Sorry.
any, yeah, it's fine. So the first letter is A, and the second part, like the regular expression represents like that the second letter can be any one of those options except A, or like the specific letter, like the specific first letter, right? What is the second like section represent? Where like, for example, you going with under the A example, like B or C or G uncountable, like what is that piece of it, like how does it connect and why
This is a union.
So shouldn't it be in the middle between the
No, I'm saying this or this or this or this regular expression is my total answer.
Okay then.
My bad. I'll.
Yeah, you rewrite it.
You want me to rewrite it? Okay, let's rewrite it. Math. That is that better?
Yeah, thanks.
Yeah, it's just one long string. Good luck writing that in one line on an exam. Okay. Let's move on to the last one of these, and then we'll have to go on to the next topics. Okay. Okay, let L4 be exactly those strings are of the alphabet ABCG that satisfies the following properties. The first symbol is equal to the last symbol. The length of the string is odd. Okay, so the first symbol is equal to the last symbol, and the length of the string is odd. Means, How do we know what the first symbol is? Again, we need to write what the first symbol is. So say the first symbol is an A. That means the last symbol is an A. The first symbol is a B. The last symbol is a B. If the first symbol is a C, I'm not writing this in one line. The last symbol is a C. If the first symbol is a G, the last symbol is a G. Okay, but now we need to make sure that the length of the string is odd. As of right now, the string is even. So if I want the string to be odd, how many characters do I have to put in the middle? An odd number of characters. One, yeah, one is odd. But an odd number, any odd number. So again, how do we do that? Do we have any constraints on what it needs to be, right? In the previous example, it could have been like I couldn't be what the first character is, but this one that doesn't say anything, which means in the middle of everything is just any odd number. So no constraints, good. A or B or C or G. A or B or C or G. So this is even. Ah, fuck it. This is even. And now one more. Let's make it odd. Now that's our answer. Oh no. Then you get the right unions next to all of them. So either this or this or this or this. And thus you get the answer. Oh fuck. There's an edge case. Ah. Okay, there's an edge case. So this would get you partial credit on the exam. Right? There's an edge case where what if the first symbol and the last symbol and odd of length 1, right? This will guarantee you has to be greater than length 3 or more, but just A alone satisfies all the constraints also, right? Because the first symbol is equal to the last symbol and the length is odd, which means on top of all of these, you also have to take into account A or B or C or G. Did you get your answer correct? Is your answer correct though? Wouldn't that mean the answer for the previous question is wrong also? This is correct because the first symbol can't be the last symbol. This one, the first symbol could be the last symbol also. What is the constraints, right? Our constraints is the first symbol is equal to the last symbol and the length is odd. This is an odd length. What's the first symbol? An A. What's the last symbol? An A. So it satisfies everything. The reason we don't get this from this is because this always has a guaranteed 3 characters, right? I'll guarantee, even if the star is equal to 0, I get one A from here, a character from here, and then another A from here. So I'm guaranteed this only works for 3 or more. Whereas one character alone could also satisfy the constraints. I don't know what you're. The previous symbol said it has nothing to do with the length of it, right? It just said the first symbol is different from the last symbol. How could any of this? Why can't first character satisfy? How is if my first symbol is an A, if I only have one character, how can the first and last symbol be different? What's the first symbol? An A. What's the last symbol? An A. They need to be different for part C. But they're the same if it's a single character.
Question, where it says B or C or G, and the second set where it's B or C or G, does that mean there's 3 characters or is it still 2?
What?
So you see how like on like for C, like the second or any of them, where it says A parentheses B or C or G star, and then B or C or G, right? What is like the second one represent of those?
This? Or this?
In part C on the PDF.
Oh, I'm looking at the PDF?
Yeah.
Okay, what was your question again? I was looking at the
Yeah,
whiteboard.
sorry, my bad. So you see how like that where the cursor is, right? Where A or yeah, that line right there. You see this like where the cursor is right now?
Mhm.
What is the purpose of that specific set in the question? Like I understand the first part, right? Like what's to the left of that.
The reason is the star. Right? This star means it could be 0.
Yeah.
But if
For
it's
the
0,
first one or the second?
this star
Yes.
applies to this,
Yes.
which means this can repeat any number of times, including 0.
So then what's the point of the second one, like right after?
To guarantee it's not 0.
Oh, okay, yeah.
We don't want
makes
0, because if we only had 0 characters, then we'd have a length of 1, which means the first and this last symbol would be the same.
Okay. That makes sense. Thank you.
Yep. Okay. We have to move on to a new problem. Let's do these real quick and then we're gonna call it for regular expressions. Okay, so this one says let L1 be exactly those strings over the alphabet A, B, C, G that contain a substring. Excuse me. Of at least one of the following strings: A, G, G, C, B, B, B. Right. So we need either one of those as a substring, which means we need to guarantee they exist. So either A, G, G exists or C, B, B, B exists. Right. So when I get to this point in my regular expression, one of these will be true, and then therefore it satisfies the constraints, which means anything can come before, and then can anything come before it? We still have 2 blanks, the before and the after. And so we need to figure out, can anything come before it? We've already satisfied the constraints, so that means anything can. So this can just be A or B or C or G. And then anything can come after it. And therefore this is our answer. Cool. It's just a substring. We've guaranteed the substring is here, which means all the blanks we just fill in with anything. And then this one says, the purpose of the star is because we said anything, right? Because nothing could be before it. Exactly, right? This could be 0 if we wanted it to, but could also be anything else. It could be anything, right? By definition, like that was the first thing that we covered, like how to say anything in regular expressions, right? So we just want to say anything. It can be there. Anything can come before, anything can come after. So it's also possible to be nothing. Yeah, exactly. This one says substring of each of the following contains both of them, basically. Right, so we both need an A, G, and we need a C, B, B, B. Right? We need both of them. And so let's put both of them, right? They don't need to be next to each other, so we can say anything can come before it. And then anything come before both of them, anything come in between both of them. And then anything come after both of them. Right? But it didn't say that AAG had to come before this, right? So that means also if CBB came first, we need to take that into account. AGG. And now same rules apply. Anything can come before it. Anything can come after it. Anything can come in between it.
I have a question.
Yeah.
Why do we keep doing this thing of anything can come before it, after it, and in between it, if it's not like stated in the problem?
Yeah. Because your regular expression needs to be like needs to be able to produce every possible string that follows the pattern. Right. So I need to figure out a way to write like every combination of strings that work. So this part here represents any possible thing that could be in between the two characters. And I know that no matter what this is, my string is still going to be valid. Right? No matter what gets generated from this, my string will still be valid. No matter what gets generated from this, my string will still be valid. And no matter what, and there's no other possible things that could be valid that I don't generate. Right? This regular expression needs to represent every possible. I guess I didn't even explain what a regular expression means. Do you guys know what like a regular expression means in general?
Isn't it like a password? That's how it is. I always understand. Like you need to make a specific pattern.
Yeah,
match.
it's a pattern. So for example, if you you wanted to know if like a phone number, right? A phone number, let's exclude area code, right? That means you would need to see like a number that is of 12 digits, right? No, 10 digits. Right. So either, but like what if someone gave you like a phone number like said 191 222 777, right? What if they included the hyphens, right? What if they didn't include the hyphens? How do you know like it's a valid phone number, right? You have to create a pattern that will like match both of these. And that exists, right? We're figuring out a pattern that fits every possible string that satisfies this thing, right? And our thing has both AAG and CBBB in it. Cool.
Shouldn't there be like
What?
What the fuck was that?
my volume must? Okay, well, what was this one? Shit. What did I say? Hello?
Are you asking a question or
Yeah, what question did I just?
you're asking me what your question was?
Yeah, that made me.
He lost his
Oh.
train of thought because of that weird this shit.
Yeah, no, well, whatever your original question was, did that help?
Yeah. I
Okay.
just want to clarify. So, oh wait, no, there was one question. So why is it not a thing to include lambda into each of those A union B union C union G star things like in between?
Right. Okay, I could take some time to explain that and then move on to the next question, right?
Okay.
And you wanted or lambda, right? So let's say the star was equal to 2, and then let's say the first one gave me a G, the second one gave me a lambda, right? What is this equal? Just G. What is the point of having lambda in this? If I didn't want to choose anything, then I would just not choose it. I would stop choosing things. Right. So this is equivalent to the star being 1 and never having a lambda option.
Oh. Oh, literally, oh, okay. It would never make a difference if I did that.
Exactly. So technically, if you did add lambda in all of these, it would still be correct. It's just kind of in the stars, it would still be correct, but it's kind of
It's just useless.
useless. Yeah, exactly.
Okay. Okay. Get it. Thank you.
So let all three be exactly those strings are of the alphabet A, B, C, G, whose length is divisible by 3 or 4. So we need it to be divisible by 3 or 4. It's the same thing as it being a multiple of 3 or 4. And basically, remember how we did odd and even? Oh, sorry, remember how we did even? We said 2n and then we broke it down. But this is also just saying it's a multiple of 2. So a multiple of 3 is just 3n, and a multiple of 4 is just 4n, right? How do we do 3n? It's just A or B or C or G, A or B or C or G, A or B or C or G star. And then the same exact thing, but 4x for here. And since it can be a multiple, divisible by 3 or 4, we would just put a union in between it, and then that's our answer. Does it make sense? Cool. Yeah, have fun. So then the next question is where the number of C's is greater than 2 but less than 5. So that means we have 2 C greater than 2. So that means 3 or but less 3 or 4. Just 3 or 4 C's because it has to be greater than 2 but less than 5. All right, so we need to guarantee 3 or 4 C's. And so what we can do is we could say we'll have like all 4 C's, but one of these C's will be optional, right? If I say or lambda for this one, then if I want it to be 4, then I take the C. If I wanted it to be 3, then I take the lambda. And now all I have to do is fill in all these blanks. And the question is, what can come in the blanks? Technically, you can do that. You have to be pretty verbose on her exams if you're going to do something like that, because if she wants to be annoying. I've seen her do that in her answer keys, so technically she should accept it. Yes, anything that's not C's. So A or B or G star. 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 Right, so this will get you 3 or 4. Cool. For the previous question, what's the divisible by 3? What if the star is 0? Then we get an empty string. Yeah. What's 0 divided by 3? 0. This is good. Divisible just means there's no remainder. So like 1 divided by 3 is 0, remainder 1. Yep. Okay. Let's move on to cardinality. Like these questions here. This should be a fairly quick topic because there's not a lot. But all you need to do is learn some of the rules. So we have a language over here, and it's a pretty simple one. So A or G or lambda, B, C, H or lambda, right? So the first question says the set of all subsets of sigma. This is equivalent to just 2 to the power of whatever the size of sigma is. So what is sigma? Sigma is right here. It's A, B, C, G, H, which is 5. So this is equal to 2 to the 5, which is equal to 32. Okay, this is a set of all subsets of sigma that have exactly one element. The way I do subsets, set of all subsets, is I use like Pascal's triangle. So like if you can draw a Pascal's triangle and then just go to the row that you need, so then this answer becomes very easy. So this says, so the way you use Pascal's triangle for this question is the row that you look at is the size of your set. So we're looking at the 5th row. And what the numbers represent is the number of subsets of that size. So this says the number of subsets of size 0, of size 1, size 2, of size 3, of size 4, and of size 5. 0 and 5 should make sense, right? Obviously, there's only one way to have an empty set, and there's only one way to have everything. But the number of ways you could have just one of everything, like have of size 1 or of size 2, of size 3 or 4, one also is easy. But like some of the if this number was just the question was just slightly more difficult, using Pascal's triangle could tell you it very simply, right? So if this set like of size 2, you just go to 2 on the 5th row, and then that's your answer 10. But this says of size of exactly 1, which is pretty simple to do in your head. It's just equal to the size of the set, but the answer is 5. I just use Pascal's triangle because if the question just, yeah, we're going to the 5th row because there's 5 elements. Yeah. And then we're going to the second number because, or the first number because we want of size 1. And this, you do 0, starting at 0 counting. So that's a pretty foolproof way of solving any of these set of subsets questions. Then this says set of all strings over sigma. So set of all strings over sigma is always infinite and countable. The way we know this is because of the reg expression that we've been writing, right? So for alphabet is A, B, C, G, then set of all things is just A or B or C or G or H. And with the star, right? Looking at this, we see that there's a star, and so therefore it's infinite and countable. So therefore the answer is infinite and countable. Here it says set of all strings over sigma whose length is equal to 2. That means just, what if we're looking at this regular expression here? Well, we have 5 options for the first character and 5 options for the second character. So therefore this is equal to 25. So 25 is the answer. And then it says set of all infinite languages over sigma. So this is where like I have a cheat sheet for how you answer any of these questions. You're gonna find the question and there's going to be like a flow chart you follow. So set of all, and then whatever comes here, if it's this could be languages, or it could be grammars, right? Set of all languages or all grammars or anything is either infinite or it's finite, right? Some finite number. If it's infinite, then there is an infinite and uncountable number of them. If it's finite, then there's infinite and countable. And if this is the set of all of them, that means it's a combination of both of these, which means set of all languages or all grammars is infinite and uncountable. Right? So for this question here, it says set of all infinite languages. So set of all infinite languages is infinite and uncountable. So infinite and uncountable. Set of all regular languages, that's the same thing as finite. So slash regular. So that means also it's infinite and countable. Are there any more cardinality questions, like infinite questions? Okay, up here. Those are different. Okay. But this flow chart is all you really need. And then whatever you fill in the blanks over here with, it doesn't matter as long as it's not strings. Strings doesn't apply to this. So we had a question over here that said strings. Strings are always finite, so there's no infinite strings. But basically, you'll say a set of all languages, and then if it has a description like this one says infinite, you just follow. If it said finite or regular or anything, then it's this. And then if it just said set of all languages, then you would know it's infinite and uncountable. Can you repeat why 5 is uncountable? Yeah. Set of all infinite is this. Just follow the graph. Okay. And then this is L, size of L. So that means we're looking at the right expression that we have. So we have 3 options for the first thing and then 2 options for the second thing. Just because this option has 3 characters in it doesn't change that it's just one option, which means that our answer is just 3 times 2, which is 6. Right, so 6. Now it says the power set of L, right? Remember we said the power set of L is just equal to 2 to the size of L, right? So this is just 2 to 6 to the 6th power, which is equal to 64. Cool. This is L star. Doesn't matter. We see a star. We know it's infinite and uncountable. This says power set of L star. Well, the power set of anything infinite is uncountable. So this is automatically infinite and uncountable. This is set of all elements of L whose length is equal to 1. So now we're looking specifically at L. And L is pretty small. So what we're gonna do is we're just gonna write out all the possible strings. Right? There's only 6. So first one is just A, B, C, H, and then A, then G, B, C, H, G, or just B, C, H, or lambda. So these are my 6 strings. And now it says set of all elements of L whose length is equal to 1. There's only 2 of them, A and G, so my answer is 2. Set of all elements of L whose length is equal to 3. There's only 1 of them, so my answer is 1. Set of all elements of L whose length is equal to 4. There's only 2 of them, so the answer is 2. This says in L, but not in A star. All right, so remember, A star is any number of A's, including 0. So how many strings are in A star? A is an A star. Lambda is an A star. But all of these are not an A star, right? They all include characters that aren't A's. So therefore, there's 4 strings in L that are not an A star. This says in L and an A or B or C star, right? So all we need to do is find any strings that are only made up of A's, B's, and C's, right? There's this one here, and there's this one here. Remember, the star can be equal to 0. So that means nothing, lambda is also part of it. So therefore, this answer is 2. This one says NL, but not an A or B or C star. This is just the complement of this. So whatever we got for this, it's just the opposite for this. So everything that we didn't choose, these other 4, is just the answer. Same thing with this one. So in L and in G star. How many strings are in L and G star? Well, there's a G, and there's also the lambda. Right? Star could be 0. In L, but not in G star. It's just the complement, so everything that we didn't pick, so those 4. And then that's that. Cardinality questions are pretty easy. As long as you memorize this chart here, know how to do power sets, and then maybe if you want to, or if you have a different way of solving this subset question, there are other ways of doing it. I don't do any of them. I just use Pascal's triangle. But if you do that, then these are 3 points. 14 again. So in L, but not in A star. So what are all the possible? So looking at just these 6, this is all that's in L. Right. So what is in A star that's not an L? Right. So A is an A star. Lambda is an A star, but everything else isn't. Which means this is why our answer is 4. Okay. Cool. Let's any questions? Otherwise, we're gonna move on to context-free grammar. Yeah, so yeah. So if you know the size of the subset of the set and then what subset you want, you just can use Pascal's triangle to go directly to it. And then immediately get the answer. There are like some obvious like things, like if it says 1, then it's equal to the size of the set. Right. So how many subsets of size 1 can you have? Well, that's just A as my first subset, B is my next subset, C is my next subset, G is my next subset, and then H is my next subset. So that's obviously 5. And if you notice Pascal's triangle, if you go down the diagonal, the first diagonal will always be 1 because there's only one way to have nothing. And then in the second diagonal, you notice it'll say 1, 2, 3, 4, 5, like etc. But rather than even knowing any of that, if you just blanketly learn how to generate Pascal's triangle and then just use that, you can get the answer pretty foolproof. You also aren't allowed to use exponents, right? So if she's like, it's stated right here, remember for all these, I said it was like 2 to the 5. Power set of this is 2 to the 6. You have to write them out. She will dock you points. Don't get why, but it's her. Okay. Any questions before we move on? Yeah, we're doing grammars now, unless we have questions. Don't forget. Yeah. Okay. So the way we're going to generate grammars is you're gonna think of this as like a compiler, right? Say I write a bunch of code, let's say like let's say I have A as a function and then I have some code in it. Right, and then somewhere else there's like a B function. Right, and then inside that B function, maybe I call a C function. And so somewhere in my code, I now need to write whatever C is. Write it as some code. Somewhere else, there's going to be like a main function. Right, and then in my main function, maybe I call A. And then maybe I call B. And then, I don't know, maybe I end. How does the compiler know like what order it needs to do anything in? Well, the compiler has some definitions that it has. Similar to grammars, we have this definition right here. So the first definition is G, right? G is equal to, this will always be the same, V sigma P and S. So V represents your variables. Think of your variables as the names of these functions. So we have main, we have C, we have A, we have B, right? Those are your variables. Sigma is your alphabet. Think of this as like whatever lines of code, like whatever symbols you're allowed to write. So like if statements, how, like all of that, that's part of your sigma. That's your building blocks of the language. So for us, our only building blocks is just A, B, C, and G, or whatever symbols are necessary, whatever characters are necessary. P is your production rules. Production rules tell us, hey, starting from main, like do this code, then call function A. Function A will do this code, and then go back to main, continue doing the rest of this code, then call B. B will continue this code, then call C. C will do this code, go back to B, finish this code, go back to main, finish this code, and then be done. So your production, P is your production rules. It's how the code is going to be followed. Your grammar is going to be followed. And S is your starting point. S is main, right? How did we even know to start with main as our first function? It's because main is built in as like a keyword. For us, our keyword is S. S is our starting point. Okay, that's everything. That's the machine, that's the grammar. But now we need to define all of these specifically for whatever language we're trying to represent. So did everyone understand up until this point? Or any questions up until this point? We're just simulating how to G is grammar. G is grammar, right? This grammar is built up of variables, sigma, your production rules, and your starting point. That's it. This will always be the same. This never changes. Technically, this changes, but for as of right now, this will never change. Okay, so let's move on to actually solving this question. The order is always exactly the same also. Yeah, V sigma PS. So let's look at this question. Okay. So we need to figure out a way to define this. So what we're going to do is we're going to say, okay, let's have a function that'll help us figure this out, right? So our goal is to print the whole thing out, right? Similar to main, our main function will, by the end of it, solve the whole thing. It may call on other functions to help it, but by the end of this, S will have generated this regular expression. Right, but we don't want everything in the main function. We want helper functions to make our code look clean, right? So let's say A is going to solve this part here. And then there's a star here. So the star we're going to represent using recursion. And we know recursion needs its own function itself, right? Because in order to recursively call a function, that definition is another function, right? So we'll call this B. And this is just to handle the recursion that's out here. But then inside we see that we have another star here. So let's call this D, right? The reason I'm skipping C is just skip C. You don't use C as a variable name. Right, but if we need more variables, we can come back and add more variables. But for now, I think this is a simple enough breakdown. So S is going to generate the whole thing. S is going to say, hey, whatever A gets, concatenate it with whatever B gets. B is going to say, okay, I'll handle the recursion, but D, you'll handle this part here, and then whatever is inside, we'll figure out where to put it. Yeah, so let's start it. So we have our grammar, and so we know what variable. So let's say whatever variables we're using. So grammar is in parentheses. Parentheses is because this is a tuple. This isn't changing sizes, right? This set, V is a set, so it can be any size. So we know that S has to be here, and we're gonna call A, and we're gonna call B, and we're gonna call D. Let me just do it exactly how she does it, so that way it's not confusing. Okay, so she says E is this inside part. And I'll clarify. Oh, fuck, wait. Let me just try to match this exactly how she does it. That way, you aren't confused. Okay, B A A B B B C over. Oh yeah, no, I had it correct. Oh, okay. So D is all of this. And E is this. So D is the right side of the union, and then E is this this star here. And as we go through, I'll clarify everything. Okay, and then so we defined V, and now let's define E, sigma. Yeah, but I'll get to that. So now how do we say what sigma is? Well, sigma is just whatever characters we see. We see an A, we see a B, we see a C, we see a G. So it's just A, B, C, G. And then we have that done. So now P, our production rules. So our production rules are how we're going to go by. So starting from the main function S, we're going to say S is whatever A gives me, I'm just going to concatenate that with B. So whatever this part is, I'm going to concatenate this with this part. And then I'm going to call it a day. And then that's what I'm returning. But now how does A do its part? Well, A says, I need to figure out, I need to choose either between CGA or AAG. And so the way you do that, you just say CGA or AAG. So this is now your union, the vertical line. And so that's it for A. And now B says, okay, well, I have to handle recursion. So the simple way to handle recursion is just do BB or lambda. Yeah, there's no unions in grammars. So the moment I do BB or lambda, I no longer have to worry about recursion anymore. I'll explain how this does it, but for now, yeah, let me just do that now, right? So I need to figure out a way that this B can represent any number of B's, right? Remember, this star represents any integer, right? So how can I use one variable to represent any number? Well, I'm saying that this B has the option of turning into two B's if it wants, or it has the option of turning into a lambda. Right. So let's really quickly, let's just do like B star. Let's use A star. Right. And let's say B, we want to define A star, so we're gonna do B turns into BB or lambda. Oh, order doesn't matter here. And then let's say A. Right. The reason this works is because say I wanted to represent create the string AAA. Starting with one B, I can turn that into two B's. I have that option. And now both of these B's need to be defined, right? And each B has an instruction, either pick BB, lambda, or A. So let's say the first one picks BB. And then let's say the last one picks an A. But these are still B's, which means I need to define them. Let's say this picks an A, and then this picks an A. So now after I've broken it down all the way down to letters, It's AAA. I've turned it from variables into the letters. The reason we have lambda is to handle this as 0, right? For example, if I wanted A star to be equal to lambda, then B would have to turn into lambda. There is another way of doing this, and it's right here. But I'll explain that also. Yeah, star could represent as BB. Right? Because I'm basically saying I can, like, in my definition, I can turn one B into two Bs. And if I can just do that, I can turn it into any number of Bs. It's kind of like induction. But not really. That seems like an unnecessary way of looking at it. But this
Question,
works. Yeah.
So, you know, in the first part, you just BBA, or you don't need the A in that case, or do you need it in both? Because here it's BB or lambda or A, so you had A. What you wrote on left, isn't it like BB or lambda? So like, would you not need the A in this case, or?
I'm not done.
Ah, sorry.
Yeah. No problem. But what is our base case? So imagine this as our recursive statement, but now our base case is either we need to figure that out, right? So what's inside of this? Either inside of B, either I'm choosing BC or I'm choosing all of this, right? Either the left side or the right side of the union, right? Remember, this is too difficult for me to figure out right now. So I'm going to use a helper function to figure it out. But this BC is pretty simple, right? Either I pick BC or I pick AAE, or I pick D. Right, you use D here. Okay, right. I'm saying inside this part of B, once I'm done with the star, which I've already defined here, what does it turn into? Like, what is my equivalent of an A? Right here, I have two options. Either it's a BC or it's this right part here, which I'm now defining as D. And D will figure that part out. And then in D, we can then figure D out. So even in D, we were just like, all we do is write two A's and then say, hey, let E figure out whatever this part is. And now E needs to figure this part out. So we could follow this exact rule here and say EE or lambda. And then what are my base cases? Either I'm choosing a D or I'm choosing a G. So we could do D or G. And this is it. I've defined all my variables. And so this is my complete answer. If you notice, this E and her E are different. So I'll also explain the other way you could do recursion. But this EE or lambda, or this like just the double variable or lambda, automatically will handle the star. But I can show why this works also. But is everyone good on this answer? Or does anyone have any question on this?
Yeah, for D, why is between AAE, sorry, between AAA E, like why is there no union then?
For what?
For D, why is there no union between AA and E?
Why would there be a union? Where do you see a
'Cause isn't
union?
it- Oh, yeah, okay, thanks.
It's okay if we make D or G star be equal to D instead. So remember, we need to, yeah, you could have saved one variable. I think the point of your question is, we could have saved one variable, but is it okay if we make D or G equal to D instead? Yeah, but that would require like changing it a little bit, and I'll do that very quickly. So up until, so the only things that change is B and D. So this changes to B, turns into BB or lambda or BC or AAE, AAE, and then we completely remove D, right? If we completely remove D, then all we have is just E turns into EE or lambda or D or G, right? This saves a variable. If you look, D is a very simple variable, a very simple helper function. It doesn't actually do that much. It just writes two A's and calls another function. But I was just going off of her. Like originally, I only wanted four variables, so I was gonna do that. But it doesn't matter how many variables you use, more or less, it doesn't matter, as long as you get it correct. I just thought that might be like it'd be easier to explain it the way it's on the answer key.
I got a quick question.
Mhm.
Sorry, my mic is bad. I'm on my camera mic, but so how we do it on variable E, on her answer, would we be able to do that on variable B as well, or no? Like that kind of method?
Yeah. I didn't explain this yet, so I can do that now. So, let me rewrite this as how she writes it. So, right, the other way of doing it is like if I wanted to represent this, B turns into B, A, or lambda. That's what's saying. These two things are equal to each other. And the way this works is, right, I did the whole, like, if I still wanted to generate BA, three A's, starting from B, I turn into a BA, and then I turn this B into a BA, and then turn this B into a BA, and then I turn this B into a lambda. And then all I'm left with is three A's, which is how I get this. So that's why both of these work. And you also can use either one anywhere. But I think this is just easier to just blanketly accept and just move on, right? Like this seems a little bit more intuitive. But they're both correct. Yeah, so if I wanted to like change this, it would be like BCB or DB or lambda. But I'm not gonna explain how I went from this to this. Just if you learn how to do it like this handles the recursion. These are your base cases. This handles your recursion. This is your base case. Then it's pretty simple, in my opinion. Let's do more of these. We'll do this one after. One more regular one, and then we'll go into context free. Context free is very simple. Is this not? Oh, I did that. Okay. Let's do this regular expression. This one looks harder. It's not really, none of these are really that much harder than any of them because it's just, if you are able to break it down, then you're able to answer these fairly simply. Okay. So let's break it down. So first thing is S, right? Our goal for S is to create this, but this is too complicated. I see that there's a star here. So let me break it down right here. Let's say A is going to handle all of this. And B is going to handle all of this. And then all S is going to do is going to take the A and the B and combine them together. But A has a star, so that means, so what's inside of A? We have this part here, which we can call, let's call this D. And then, or we could have this part here. Let's call this E. And then in B, we have three options, either this, this, or this. These are simple to write. This one requires definitely another variable, so let's call this F. And if we need more variables, we'll come back and fix it. But for now, this looks good. It doesn't actually, we'll definitely need more variables, but it's intentional. So starting from grammar, all right, what do we put here? This is always the same. This is always going to be V sigma P S. And then V, right? B or C is not a variable, right? Yeah. Smart. We do have to fix that, but we let's start. Let's just start, because we can always come back and fix this. This is our notes, right? This isn't even part of the answer. So if we need to add more variables, we'll add more variables, right? So let's start with this. So S, we know that we're going to use an A, we're going to use a B, we're going to use a D, we're going to use an E, and then we're going to use an F. And then if we need more variables, we'll just keep it open, right? Who cares? Yeah, and now sigma. How do we figure out sigma? Well, I see an A, I see a B, I see a C, I see a D, and nothing else. So that's my alphabet. Okay. And then now for our production rules. Our production rule says starting from A. Starting from S? S is only going to say A. Whatever A gives me, concatenate with whatever B gives me. So S is just A, B. But now how do I, yeah, nice. And then how do I define A? Well, A is a star, right? And then I said A is going to be, so handle the star is just AA or lambda. And then what's inside of A? Well, A has two options, either pick D or pick E. So that's my base case, is either D or E. And then let's define B. B says, well, either I'm picking A, B, or I'm picking DCC, or I'm picking F. F is this whole thing where we need a helper variable for it. So let's say AB or DCC or F. Okay. Let's let's define E. Right. E says, well, E has a problem, right? We don't have anything to define this B star, so we need another variable. So let's call this H. Right. I'm skipping G because I've already used G. So H is going to handle the B star. We definitely need another variable for that. So this is just going to say DHC. And then H is just a star. So let's just do HH or a lambda. And then, or my base case, which is just a B. Okay, so that's done. But now we need to define D. So let's do D. D says, well, A, and then, oh, we have a star here, so we need another variable for this. So let's call this I. So AI. And then I is going to be another variable that's recursive. I mean, that's a star, so let's do the recursive. So I or lambda. And then what's my base case? Either I'm picking a B or I'm picking a C. Okay, so now I is done. And now we have all of this done. But we still didn't define F. Let's define F. F. It's a star. So let's just do FF for lambda. And then what's my base case? Well, it's just ABBA. I mean ABAA. Cool. I realized I needed two more variables. I definitely could have done this in less variables, but it doesn't matter. If you look at her answer, she does this in H. She uses one less variable than I do. Even that's more than absolutely necessary, but it doesn't matter. And this is our answer. Was that clear? Was there any questions on that? Oh, you guys are emoting. That's what that is. That's cute. Yeah, right. I mean, even think about this logically, right? Like, why would I have a massive function that does a bunch of things? That's going to be so hard to code up and be very annoying, right? Imagine something breaks, right? Rather, if I just have everything in different helper functions, then it's very simple to break down. It's very simple to understand. It's very simple to code. Yeah. So, um, should we do another one of those, or can I move on to the next topic? Next topic. Oh man, if you guys thought this was easy, the next topic is telescoping, which is even easier. Where the fuck is the telescoping question? Ah, here. This was context free. No, it's actually easier. It's actually easier. So like the hard part of context free is figuring out where to put the brackets. But because this is telescoping, the brackets like kind of are defined by themselves. So like already for you, which means it's even easier. And the pattern is even easier. So let's look at this one. Yeah, it does look harder, right? But it's actually so much easier. So after this, the only topics left is finite state automatons. So I'll cover that, and then that'll be it for the review. These are kind of fucked questions, but
So the one that you said is like barely even worth it.
yeah, definitely don't even do it. But I'll teach it. Someone said, "Can you make the picture?" My bad. Someone said, "What this picture?" Yeah. Okay. What was your question?
So if we're good on everything but the automaton thing, we could still get a 100 if we're good with everything else. Because it goes over.
Oh no, automatons are pretty easy. I meant this question is fucked, right? This one right here. This context free grammar question here is absolute dog shit. I'll go over it at the end, just to show you how much of a dick of a question it is.
Can we do another context free example?
Bro, everyone just said it was easy. I already pulled this one up.
Damn.
This is a context free question anyway, so I'll do this at the end. So maybe that'll suffice. Okay. Give me like 1 minute. Okay. So the way you answer these questions is, this is not a regular expression. This is a like a template on like patterns for how the strings need to be generated, but this is not a regular expression. Basically what it's saying is this number of G's and then this B's are related, right? because this is G to the L. So whatever L is, I'll have twice as many B's here because it says 2L. So these two things are linked together. This N here, and then there's an there's an N over here. So these two things are linked together. There is an M here and an M here. So these two things are linked together. There's an A here and there's a J here and a J here. So these two things are linked together. And this is by itself. There's nothing linked to it. But that's it. These are your brackets. I have like a bracket that spans the whole thing. So we call that S. We call this A. We call this B. We call this D. And then we'll call this E. Not linked to anything. So the way you now write your grammar is you work left to right, outwards in. So let's do that. And then the pattern for writing them is even easier. So G is equal to V sigma P S what comes up? Oh, V, right. So we have a S A B D E. Our sigma is equal to, don't get confused with the exponents. It's only just A, B, C, and G. The K, the J, the N, L, those aren't your letters. So don't make that mistake. Oh, I'm actually I was making like video, so I went to go check on it. That's my dinner. And then P. Right? So P, you just follow the rules. So S. So the way you do it is, now we need to actually figure out what these even say. So let's look at this as an example. Right? It's saying A to the 3n plus 2. This is your coefficient. This is your constant. The way we create these is the coefficients go with the recursive statement, the constants go in your base case. Regardless of what n is, we'll always have at least 2 A's. And then any multiple of 3 A's also. So this G to the L and this B to the L, we have our recursive statement and our base case. So our recursive statement is whatever is on the coefficients. So there's a 1 coefficient here, so just 1G, and there's a 2 over here, so BB. Right, so this is in the front, this is in the back, and then our recursion is in the middle. All right, so this G is from 1G here, and then 2 B's in the back. And then our base case is whatever the constants are. There are no constants here, but then what's inside of it? Inside of it is an A, so our base case is A. And then we just do that again. So A says, our recursive statement is look at the coefficients. I see that there's a 2 here, there's a 3 here. So that means 2 A's in the front, 3 A's in the back. Our base case is the constants. There's a 2 plus 2 here, so 2 more A's. There's a plus 2 here, so 3 more A's. And then what's inside of my A? A B and a D. So B and D. And then let's do B. B is A to the J and then C to the 2J. So my coefficients are 1A in the front.
D come before B.
Doesn't matter the order. Oh, D would come before B. Yeah. I thought you meant the way that I was writing the grammars. Yeah, D does come before B. Okay, so then I have an A in the front, and then for B, I have 2 C's in the back. Why is it 3 A's when it's 3n plus 2? Oh, yeah, I'm pretty retarded. School. Yeah, constants, so this should have been 2. Okay. So Yep, so this part's done for the recursive statement. Now for the base case, what are the constants? There are no constants here, and there's one constant here. So that means just what's on the inside, so E, and then followed by one more C. Right, nothing over here because there's no constants here. And then let's define D. D is C to the M plus 1, B to the 2M plus 1, plus 3. So my coefficient is 1C in the front and then 2 B's in the back. And that's it for my recursive statement. Now for my base case is just plus 1C. So 1C and then 3 B's. There's nothing in the middle of it, so this is done. And now E is the only thing left. E is just this B to the 4K plus B to the 3K plus 4. So just 3 B's in the front. E and then 4 B's as my base case. That's it. Are there any questions? Cool. The only way this could change is if you weren't given an S to begin with, right? So if I look at this example here, there's no bracket that spans the whole thing. So on top of whatever I have here, I need to make one more that spans the whole thing. And so if I call this one A, and then this B, and then this D, S would span the whole thing, and then S would be made up of A, B, D. So the right is always base case. Yeah. It's the order doesn't matter, but just keep it the same. So yeah. This is your recursive statement, this is your base case. Recursive statement, base case, recursive statement, base case, recursive statement, base case. The only difference with this problem and the previous one is I didn't happen to get lucky and have something that spans the whole thing. So I need to then set that up. So S was going to say concatenate A with B with D. That's this part here, this part here, this part here. And then defining everything is still the same, right? This is A, which will have the coefficients and the constants. B has same thing, and then E is inside of it, and then inside of E is H, which is the A to the 3K plus 4. 3 A's, 4 A's here. That's your recursive statement, your base case. And then, yeah, that's it for this one. Make sense? You want to move on to the next topic? Or do we want to do another one of these? Okay, let's just do this one then. Okay, so let's draw the brackets. I see that these both have ends in their exponents. This has an M, where's the and there's an M over here. This is a J. Oh. M and this M. This J and this J. There is this K here. There is this L with this L, and that's everything. But I don't have anything that spans the whole thing, so let me just create one more just to span the whole thing. So that's called S. Let's call this A. Let's call this B. Let's call this D. Let's call this E. And then let's call this F. Okay. So starting from the beginning, G is equal to V sigma P S. And then right, V. Okay, so this is just S and then A and then B and then D and then E and then F. And then what's next? Sigma. Sigma is just the letters, so A, B, C, G. Don't include the exponents. And then our production rules. Right, so starting with S, we see that S is just saying concatenate A with B with D. Okay, and then how do we define A? A, you just look at the coefficients first. So for my recursive statement, I see that there's a 2 and a 3. So 2 G's in the front. And then 3 A's in the back. And then for my base case, my constant is just plus 1 G. And then let's do B. B says 3M. So my coefficients is 1 C to the M, just 1, and then B to the 2M, so 2. So 1 C in the front, 2 B's in the back. My base case is a plus 2 C's, so 2 C's. Plus 2 B's, 2 B's. And then E is inside of it. Okay, let's define E. E says B to the J plus 3, BJ. And then C to the 2J. So we have 1 B in the front, and then 2 C's in the back. And then our base case is plus 3 and a plus 3. So 2 B's, 3 B's in the front, 3 C's in the back, and then we have F inside of it. Okay, and then let's define F. F is just a to the 3k plus 4, so my coefficient is 3, so 3a's in the front. And then my base case is a plus 4, so 4a's. And now we define D. D is just this G to the L. So 1 G in the front, and then A to the 2L, so 2A's in the back. And then a D, and then 1 G, and then 2A's is my base case, and then that's it. Yeah, nice. This make sense? Any questions on this?
Yes. So for A, right? The GGA part of it, you got that from the function, right? Like in the exponent?
Yeah.
Okay, then where did the union?
Wait, I don't know if you're cutting off for me.
Hello?
Yeah, is it just me? I know I can't. You were cutting off.
Oh, what I said was that why is there the G?
Because the constant.
Makes sense, thank you.
Yep. Okay, let's move on. Mhm. Um, okay, let's move on to finite state automatons. Okay. So for finite state automatons, all you need to know is these small machines, and everything is going to be a concatenation of the smaller machines. And so let me show you all the smaller machines you need to know. So let's say I wanted to make a transition. So just write A. So from a given state, in order for me to transition, oh yeah, let me explain what the symbols are. So in a finite state machine, you have a starting state. You have one of them. You have any number of intermediate states. So it's just a circle, any number. And then you can also have multiple final states. So, and then in between states, you have transitions. So a transition takes you from one state to another. You can write anything on the alphabet or write nothing. But you can only write at most one characters. So for example, if I wanted to write ABA in a finite state automaton, starting from my starting state, I would have to have an A for one state, B for the next one, and then another for the other transition, and then I would be done. So I'd call this my final state. Okay, that's the basis of how a finite state works. But now, how do we convert a Reg expression into a finite state? Oh, and so what I mean by this, the lambda also. So like at any given point, if I really wanted to, I could have random transitions to say something like lambda to something else, right? Whatever. Like lambda is a transition also, if I didn't want to write anything. Typically, this is just used for like breaking things up and clarifying things. And so that certain operations don't overlap each other. It'll make sense when I do an actual example, but that is also a thing. You can have a lambda transition. So yeah, so let's start with some of the smaller machines that you need to know. So the first machine is what we just did. So just a concatenation like AB. So you have to use two different states, two different transitions in order to do it. Something else you need, and so that's that. But what if you had A union B? Well, from a given state, you have two options. Either you take an A or you take a B. You could also write this as just A or B, right? These are all your options, right? If it doesn't matter, like what state you end up in, there could be reasons why you do either. But if it doesn't matter, regardless of A or B, you're going to end up in the same state, then do this. If A sends you to one state, B sends you to another, then do this. The next thing is A star. So from a given state, I want to write A as many times as I want. Then it's just a loop back to that state, writing A. Something else you could do is like A, B star. All right. So from a given state, I need to write an A. No, it's not hard. This is also pretty easy, but it takes a little bit of practice. And then from here, you want to write B. So I write AB, but then how do I repeat this process? Well, I take a lambda to go backwards. Go back to the beginning. And then if I ever wanted the star to be equal to 0, I would just take a lambda to skip everything. So this represents AB. There's another way of doing this. From a given state, I could go A to get here and then B to go back. So this is also AB star. It's all up to you how you choose to draw these. But they all like are correct. Is there anything else you need to know? No, it's everything. It's a star, it's a union, that's concatenation. That's everything. It's everything you need. Think. We'll figure it out. So let's move all of these to one thing, and then what's pointing back to initial A or lambda? For AB star. This is a lambda going backwards to restart the ABs again. The reason I have a lambda down here is to skip them. And then, yeah, this doesn't require any lambdas. Okay, so let's do this example. For the star one, would the initial state and be the terminal state also? It depends on what your string is. For this specific, if this was my only string, then I mean my complete reg expression, then yes. But they're not gonna be that simple on the exam. So let's do an actual test exam and then see how that works. Okay. Let's let me just clean this up a little bit. And we'll just keep that there. Let's do this example here. I don't think we need this one. Okay, so we need to figure out a way to represent this as a finite state automaton. So let's start with our starting state. So we're starting right here. So the first thing we need to do is write A or C star, right? So from my state, I can write, oh, no. So I see that there's a union here, right? That means I have my reg expression either chooses this or it chooses this. And so I have two options. So starting from my starting state, I need to figure out, my machine needs to figure out, is it doing the top path or the bottom path? And so we'll just say that is two different states. So if I'm in this state, that means I'm doing this. If I'm in this state, that means I'm doing this. Okay. So let's use colors to, so this is the green part. So the first thing I need to do is write my A or C star. So similar to how I am combining this and this, right? I'm going to put a loop back to the state I'm in, where and I have two options for each of those characters. So from here to go back to the state is just either writing an A or a C. That handles this A or C star. So I pick the top path and then I do this loop as many times as I want. Regardless of how many times I do it, I will end up back at this state, and then I'm going to continue forward, which is writing this part here. So let's call this lambda. So I get to this state after I finish doing the A or C stars. Notice if I wanted 0 stars, the 0 A's or C's, I could literally just skip the loop and go straight to the state. Lambda, lambda, transitions. But if I'm at this state here, I've made it this far into my reg expression. Okay, and now we need to figure out how to write this part here. So again, I have a union, so I have two options. Either I write a D or I write all of this. So let's do this part first, because then writing this is very simple. So how do I write this part here? So from here, I have two options. Either I write BA or G star, right? So from my state, well, let's use the lambdas again. So top or the bottom. Yeah, so two paths up or down. So this now says either I write BA, so let's do B and then A and get to a state, or I write G and get to that same state, right? And then I'm just going to do this thing here. So lambda backwards, lambda forwards to represent the star. So a lambda going back. And a lambda going forwards. So if I chose this, that means I'm here, and then I did it, then this would be my final state. I could be done right here. At any point in time, if I make it here, I can stop and be done. And now all I do is I can just make this transition line here. Let's just make it go all the way over here. And then let's call this transition D. And then let's delete this lambda. Okay, ignore that line. I can't erase it. Okay. So this is my final state. This is my path, my top path. You can put lambdas whenever you want. And whenever you think you need a lambda, just put a lambda. Right? Like originally I thought I might have needed a lambda for this, but I don't. I saw that I could just throw a D to go all the way to my final state and call it a day. Oh no, this shit. Fuck, this is wrong. Okay. The reason this is wrong is because look, if I'm starting from here and I take the D path forward and get to here, there's a lambda transition that sends me back here, which means I could now do D and the middle part. So this is wrong. This is why you use lambdas. So the other thing like I can do is I can just make multiple final states. I'm also allowed multiple final states. So let me just make this a final state and then say this is a D transition. Rather than having them intertwine and then kinda, yeah. But to avoid any type of issue like that, let me just have multiple final states. You're allowed multiple final states. Like in this example, in her answer, she has one here and one here. So let me just have more also. Right, to avoid anything like mixing, it's easier to do that. But that's the top path. And now for the bottom path. Let's do this in pink or red. Okay. So from this state, I need to do a BG star. So that's a B and then a G. Right, so I loop back and forth, and then that handles the BG star. And then once I'm done with this, if I move forward, that means I'm writing a C. Notice if the star was equal to 0, from my starting state, I could do a lambda and then immediately go to C and be at the correct spot that I'm in. And then from here, all I need to do is write an A. And then that's it. That's the whole part here. That's this part here, but now the star. But the star I'm just going to use as a lambda going backwards from where I began. And then a lambda going forwards to where I was from. And then that's my final state. And that's it for this part. Are there any questions? We'll do more of these.
Yeah, so I got a quick question. Where would the G be? Because I don't see on the graph. Wouldn't it be
The red one or the green ones?
the green G? The G?
Oh, I undid it. Should be like, let's just put a G right here. Right, this lambda is for this transition, this G is for this transition. Yeah, I think
And
it got
the
erased.
red transition on the bottom is, or is there supposed to be a lambda there as well?
Ugh, yeah. It's been a while since I've taken this class. Okay. but does this make sense? Basically, all I did was combine these in order to make this based off of this. Okay, let's do one more example. Let's do this one. Okay, so starting from my starting state, I see that there's a star here, so I'm going to eventually loop back to the state. But from the beginning, I see that I have a choice, either BG or this part here, right? So BC or this part here, right? So either I do a, let's do lambda transition. Let's do a lambda real quick, right? Either I'm picking the top of the BC or I'm doing the bottom thing. And this is the top one, so that means it's a B and then a C. And then I get to the state. This one says D or G. So that's my D or G star, and then an A and an A. Right, so with that, whichever path I took gets me to this state, which is now at the star. Can you post the notes from this review by any chance at the end? I know it will be in the video, but for backtracking. Yeah, what notes? Okay, there's a lambda and there's a star here, so in order to do that, just a lambda going backwards and a lambda going forwards. I'm not posting the drawings, bro. This if you go back to like this and like try to like, actually you could probably figure out what that means, but like if you looked at like something like this, like it's not gonna make any sense to you. I'm like drawing as I go and making things up. It's not clear like after. Okay, we got into this point, which means we made it here. And then now we want to do this part, CGA or AAG. So from my state here, I have two options. Let's just throw lambdas. And now either I write C, G, A, or I write A, G. And then regardless of which path I took, this is now my final state. And this is my complete answer. Does it make sense? Lambda at the top and the bottom. Ah, fuck. Good call. Good catch. Yeah, it's definitely one of those things that you need to practice, but the concept should make sense based off of just knowing the smaller machines that was on the previous slide. It's yeah. Can you go over the purpose of the lambda transition again? It's just for clarity. If you remember like how I fucked up the previous question, like if I just used a lambda, that wouldn't have like, or just that I would have avoided that issue. Or like it's literally just for clarity. It's just so like it makes it easier for you. Maybe you want to just move shit over, right? Like I don't actually need lambdas right here, but I just put them in just for clarity, right? Top path, bottom path, the lambdas are just there. They don't do, they're not absolutely necessary always, but regardless, you have them. And so you might as well use them. Um, so anytime we have a cleaning star loop, we should put lambdas. Yeah, you could do that. That's not necessarily a rule of thumb, but that's not wrong. So you might as well. Wait, let me just double check. So anytime we have a cleaning star loop, we put two lambdas, one at the beginning, one for the end. Oh, you mean this for this and this? Yeah. Sorry, I thought you meant like these lambdas here, or something, or and these lambdas here. Yeah, no, that's important. It's like playing Rust. I don't play video games, unfortunately. Too short of an attention span. But what about D or G? D or G? So D or G fell into the case where it was a single character. When it's multiple characters long, or like multiple some segments long, D or G is just one character. So I could just use a loop back going back to the state. But I could have done whatever you are saying. So like I could have done like D or G and then lambda going backwards, lambda going forwards. But like when it's a single character, it's just very easy to just put a loop back to itself. It really doesn't need to be this complicated. Okay. Is there any, do you guys want me to go over more stuff? Like, yeah, we could be done for today if we're good. Oh,
Yeah. Deterministic, she went over that.
it's definitely past someone's bedtime, but sure, we can go over this. Let's do this one. Let's do B. So the only difference between deterministic and non-deterministic is deterministics don't have lambdas in it. You're never explicitly told whether or not you need to use a deterministic or non-deterministic thing. Automaton. Where the automaton doesn't exist. You need to understand theory in order to know when something does or doesn't exist. For your exam, nothing will not exist. Yeah. I'll explain some things later and like exam 2 review as to when things will exist or not exist. But for now, they all exist. Let's do this one. So the only difference between a deterministic and non-deterministic automaton is deterministics don't have lambdas. Yeah, right. For example, reason is like let's go back to black. If I had like a state and then I did like a lambda transition and then I went to this state and then let's do an A and then a lambda. Right. say I told you I wrote an A so far. Which state am I in? Am I in this state or am I in this state? Because there's a lambda here, it's free to move to the next state, so it's impossible for me to determine whether or not I'm in this state, saying I've already finished the A, or I'm in this state and I've already finished the A. Whereas if this was deterministic, then I couldn't have a lambda transition. If I told you I written an A so far, then you know for a fact I would be right here. The reason non-deterministic and deterministic automatons exist is theory. They're like any non-deterministic automaton can be converted into a deterministic automaton. There is an algorithm to do it. I've seen it on one exam, like ever. I'm not going to teach that. But no, and vice versa. They're equivalent to each other in terms of computability, which is also part of how you determine if something is exists or not. But we don't have to go through that now. Let's just answer this question. Okay. What the fuck? So this question says, let L2 be exactly those strings over the alphabet A, B, C, G that contain exactly one A and one G. Right, so one way to tackle this question is to just write the regular expression, right? This sounds like a pretty simple regular expression to write. And the way you would write it is A, G, and then B or C star, B or C star, B or C star, or it's B or C star, G, B or C star, A, B or C star, right? This is exactly one G and exactly one A. And then from here, writing this is pretty simple, right? Also, yeah, so you could have wrote this as a non-deterministic finite automaton, right? If I do that right here, right, a lambda going to the top path, lambda going to the bottom path, and then here is just a B or C star loop. And then an A, and then a B or C star loop, and then a G, and then a B or C star loop. And then that's your final state, and then the same exact thing here. But a G comes first now. You would just take out the lambdas at the end, right? What lambdas at the end of these lambdas? You can't just do that always. That's the problem. That's why there is an algorithm to solve to convert it. I'll explain how you get this answer, but not by converting this to this. But my point is, it didn't specify that this needs to be a deterministic one, which is why you could solve it non-deterministically, and this is pretty easy. But for hers, let's do it her way. Okay, so you don't need to label your states like she did here. The the thing is that the labels make a lot of sense though for understanding the answer. So this is none of like no A, no G. This is G, no A. This is A, no G. This is G and A. And from there, it makes a lot of sense, right? So you're only ever in either one of the four states, right? So if I did write a G, then I'd be in a state where I have a G but no A. And then if I did write an A, I would be in a state where I did write an A, no G. And then from here, in order to get to my final state, I now need to write a G. In order from here to get to my final state, I need to write an A. And at no given point, do I care about the number of B's or C's? So there's a B or C in all of these. Hence, her answer. Fuck, I thought this was gonna be easy to remove the lambdas. It just determines the G or it comes first, right? Yeah. So either, if you remember I had the right expression there, it was the top path or the bottom path. So, yeah. Does that make sense? This is one of the things that you should just practice doing NFAs or just finite automatons before figuring it out. So we could do this one. Right. So this is the one that says like let the total number of B's, C's, and G's, i.e. number of B's plus number of C's plus number of G's equals 4. Okay. So again, at any given state, you don't care about A's. But in order for you to go from n to 1, so none to 1 to 2 to 3 to 4, you need a B, a C, or a G in order to increase your count. Hence, that. This one is, there's no lambdas, so it's deterministic. So, but you don't need to identify these things. Like, if you just solve it, then if you just solve it however you think is best, then that's it. That's all you need. At any given point, you don't care about the A, so there's A loops on everything. This is your final state because you've reached 4. If you get to this, you don't need this. She sometimes adds this to hers. This is essentially like a garbage state, right? Notice the moment you get into the garbage state, you can't leave the garbage state. And you can never go from this state to the final state. So that's what this is. So this just means you have already added too many. And then what are the signs that we need to construct a deterministic versus non-deterministic one? There aren't any. It's just an automaton. You just write whatever you need to write. Like I showed you in the previous example that I answered this with a non-deterministic, but this is a deterministic. It's just whether or not you choose to use lambdas. That's the only difference. Yeah, preference. There is no questions that only can be solved using a deterministic automaton. But you don't need lambdas always. So like if you just happen to not use any lambdas, then it's deterministic, but you didn't intentionally do that. Okay, so this one here is just a complement of this. So this one says total number of B's, C's, and G's is different from 4. This one is equal to 4. So all she did was flip the states, right? So any starting state was now no longer a non-starting state. I mean, sorry, final state is no longer a final state, and any non-final states are now final states. So notice here, your starting state could also be your final state. That's a thing that could exist. Yep. These are some challenging context-free grammar questions. If you guys want to try them, you can try them. You guys probably will struggle a lot with these though. That's all the topics.
Hey guys, what's going on? Hey guys, what's going on? Hey guys, what's going on?
So fucking what?
Yeah, I'll upload the video probably by the end of the day.
So 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 fuck so fucking what?
Hey guys, what's going on?
Fucking what?
Hey guys, what's going on?
This is what TikTok does to your brain. This is what I imagine all of you guys have in your brains right now.